Okay, so today we are going to be solving graph problems. I mean, not solving, I'm more like I'm practicing, so I will just be explaining my solutions of everything. By now, I have practiced a normal graph, I have practiced BST, and now I am on DFS. So, DFS, BST I was not able to record, but DFS I have recorded, so I will tell you my solution and walk you through it quickly. So in this we were given an undirected graph containing v vertices. You can read this if you want to, I will just explain myself. So we had to apply DFS on this and print the output like this. So apply DFS on this and print the output accordingly. So what I did for this is, since we are given an adjacency list, so what I did for this is, first of all, I created a visited vector called visited with initially each one being unvisited, being false, that is. Then I, for each node, for each I, you can say for each. So basically the index of this adjacency list is is your node u, and each of the value in the vector of this index is the node v that it connects to, or these two nodes have an edge between. So what I did for this is, first of all, I iterated with each value of I, so that way you can get each u, and if it is not visited, then I will be calling this helper function. In this helper function, I am passing the node u, I am passing the adjacency list itself, I am passing the v list, that contains each of its neighbor, each of the neighbors of u, and I have also passing this visited. I have created a global variable called result. Now as soon as I get into this function, I am going to be putting visited of u equals true, and then I am going to be pushing the result in this result. Then I am going to be iterating all the values in this vector v that has all of the neighbors of u, and then for each unvisited neighbor I am going to be calling the helper again. So that way we have implemented DFS, and the code works completely fine. I can show it to you. Let me compile this, let me submit this quickly. So yeah, this works completely fine. So I will move on to the next question now. If my solution is not clear by any sense, you can go online, check someone else's solution, although it is just normal DFS, nothing confusing, but okay, it's fine. We will just move on to the next question now. Okay, so now I have solved the next problem as well. I will be honest, I'm still a little bit confused in this, but I will try my best to explain it. So we just have to find if there is a cycle in an undirected graph or not using BFS, and what we are going to do in this, in like using general BFS by storing the nodes in queue and also marking visited equals true, we are also going to be storing every node's parent. Why we are going to do that is so that we can find a cycle, and that how that basically works is that if a node has already been visited, then we can check if its parent so if a node has already been visited, then we can check if it is not equal to the parent of the current node. For example, we have this one, we will put it in the stack or in the queue, then we will pop it, we will put 2 and 0 in it, right? Now with 2 and 0, we will first go to 2, for example, or let us say 0. We'll first go to 0. From 0 we can store 1 and 2 in it, right? Now since we have 1 and 2, 1 is since this is undirected, 1 is also adjacent to 0. So what we can do is we can store it as the parent. Yeah. So we will be storing this 1 as the parent of this 0, and from this 0, what we are going to do, we are going to be pushing 2 and 1 in it, right? Now we are going to be pushing 2 and 1, and we are just going to check if it has already been visited or not. So what you can do for this is, you can check with 1 first, Now 1 has already been visited, but is it equal to the parent or not? It is equal to the parent, right? So it is the adjacent one. So it is equal to the parent, we won't do anything about it. Now we go to 2. Since 2 is not visited, we are going to be putting it in the queue and marking it as visited. Now from 2 we have 3 options. Let's go with 1, right? Now 2's parent has been marked as 0. 2's parent has been marked as 0. Keep that in mind. Now we go to 2. We go to first, let us start with 3. So from 2 we first go to 3. Now 3 has not yet been visited, so we can just directly mark it as visited and move on. Now we go to 0. 0 has been visited. Now we will just check if 2's parent is 0 or not. If 0 is the parent, then we know 2 came from here, right? So it is not a cycle. Then we go to 1. Now again, since 1 has already been visited, we can just directly check if 1 is the parent of 2 or not, right? Or if 1 is equal to the parent of 2 or not, but the parent of 2 is 0 and 1 is not the parent of 2. So that means it has come from somewhere else, right? So from some other direction you were able to reach this 2, and you have already been able to reach this 2 from this 0. That means we have a cycle here. So that is the simplest, basically the logic behind this. You just have to check if the parent that you have, if a node has already been visited, if an adjacent node of your node has already been visited, then you just check if it is equal to the parent or not. Because if it is not equal to the parent, that means we are coming to it from some other direction, and it is not the only adjacent one to it, right? So that way we can check if it has already been visited or not. I've already compiled this code and run it and submitted it, so I know it works. I can show it to you as well. Maybe not the most efficient way of solving it, but it works. And if it is the root, then you can just mark the parent as -1, because the root cannot really have any parent anyways. So yeah, so this works. Took me quite a few tries, so now I will just move on to the next problem. You can also try it out if you want to. Okay, so I have just solved the same problem using DFS instead of BFS. So the logic is exactly same. You just check if the already visited neighbor is the parent or not, because if it is not the parent, then it is not the one that we have come through. There is some other part that we have come through and hit the same node again. That is the only thing that you need to worry about. So the whole logic is same. Is just instead of BFS I have applied DFS. So instead of using a queue, I am just doing recursive calls, and if it returns true, I just directly return true. Otherwise I return true if the neighbor is not equals to parent. Otherwise I just return false. Simple as that. Same solution. In this I am just passing the parent variable like this, parent parameter argument, whatever you want to call it. So yeah, this works. I have compiled it and run it as well, and it works completely fine. I've submitted it already. So yeah, so this works. I have solved it. I just wanted to let you know about it, that I have solved it using DFS as well. Now we can just move on to the next problem. Okay, so I have just solved another problem. In this problem we had to find a cycle in a directed graph instead of an undirected graph. So the solution to this is going to be a bit different from undirected graph, and why that is let me show you with an example. Just a second. I hope my screen is visible. So for example, we have this, right, and the arrows are going like this. Now, is there actually a cycle here? We can go from 0 to 1, then we can go to 2, but from 2 we cannot go anywhere, right? Similarly, we can go from 0 to 2, but we cannot go anywhere. So there is not a cycle in this, right? There is no cycle in this. But if we use the previous algo, in the previous algo we were using the parent node, right? So we had a node and we had a parent. So starting with 0, for example, 0's parent is going to be -1, because obviously it does not have any parent. So then we process 1 and 2 because they are the neighboring nodes of 0. So for 1 the parent is going to be 0, and for 2 again the parent is going to be 0. Then we will start processing for 1, right? So when you start processing for 1, you will go to 2, but you will see, oh, it has already been visited, right? Let me also write visited here. So what are the nodes that have already been visited? It is 0, 1 and 2, right? So we will pop out 1 and we will check its neighbor. The only neighbor of 1 is 2. And since 2 is already visited, we can check if the parent of 2 is equal to 1 or not. Now, since the parent of 2 is 0 and it is not equal to 1, we will say yes, there is a cycle there. But is there a cycle in reality? No, a cycle is not there because it is a directed graph. And because of that, you can't go both ways. And since you can't go both ways, unless obviously you have defined edges both ways, but in a directed graph, it is not necessary that you will always have both ways. So this solution fails. So now I will explain to you the solution that works. So just a second. Yeah, so in this, what I am doing is I use another array which was called DFS visited, or you can call it like DFS path, whatever you want to call it. So what it is going to do, it is going to be tracking all of the elements that are in the current DFS path, right? And we will use it with current visited node. And why we do it is because, for example, again let me show it to you using paint. For example, if you have this cycle here, let me create a cycle 0, 2 and then 1, right? There is a cycle here, and if we are in a DFS path, for example, first we visit 1, then we can mark 1 as visited. I'm marking it like this right now. Then we will go to 0, we will mark it as visited. Then we will go to 2, we will mark it as visited. From 2, we will go back to 1, but we see, oh, it has already been visited in the current DFS path. What does that mean? That means that we have hit a cycle because we are going back to the previous node, right? So that is basically what we are doing. And why we are using a visited vector still is so that we can avoid processing the same node again and again. That is the only reason. So it is to avoid basically being stuck in an infinite loop, because if you don't mark them as visited, for example, you will keep going in the visited condition again and again and keep processing all these nodes infinitely basically. So that's why the visited node is used and the DFS path is used, so that we can check if there is a cycle or not. Now I will quickly explain it to you. So the solution is quite simple. We visit, first of all we create obviously however we want to create our own graph using the initial edges that we are given, the edge list you can basically call it, and then we create the visit and DFS path. Then we will be iterating each node, and if it is not visited we can call this DFS function on it. In the function I'm going to be marking the node as visited and as being in the path itself. Then in the for loop we will get each of the neighbors and we will check if it is not visited or not. If it has not been visited yet, then we can process it. So we will just call DFS visit DFS on it again, and if it returns true, then we can return true, because it will only be returning true in case we have found a cycle. So you just directly return true. Otherwise, if the node has already been visited, then you don't have to process it again. But what you can do now is you can check if that node is in the current DFS path or not. If it is already in the current DFS path, that means we have it a cycle, and then we can return true. And when we come out of the loop, we can just mark the current node as node being in the DFS path. So we are basically backtracking from here, and we'll mark it as false and return false. That is basically the solution. This works completely fine. I have tested it out. I have submitted it as well, so this should work. Now this is finding a cycle in a directed graph using DFS. There is a BFS approach as well. I will learn it and then tell you the solution for that as well. For now, I will just move on to the next problem. Okay, so I have solved another problem. This time I basically found the topological sort of a directed acyclic graph using DFS. So I think first I should tell you what a topological sort is. So basically, it's a linear ordering of vertices such that for every directed edge u to v, u comes before v, right? So you in the topological sorting or in the linear ordering, you just have to make sure that an edge always comes. The parent edges always comes before the neighboring edges, you can say, right? And why we need to use a directed acyclic graph is, first of all, let me clarify the directed part. Since in an undirected graph, the direction is not clear, so you won't be able to tell which edge comes before, right? So obviously that part is kind of cancelled out. So we need a directed graph. And why we need an acyclic graph? Because just a second, let me show you using paint. So I hope my screen is visible. So for example, you have this 0, it goes to this one goes to like 2, and then this 2 goes back to 0, for example. So you will go to the 0, yeah, so 0 should come before 1, right? So you will put 0 before 1, then you can put 1, and then you can put 2. But okay, now 2 is also going to 0. So 2 should come before 0, but as we can see, 0 is already before 2. So the topological sorting completely fails, right? Because of cycle. So that is basically why we need a directed acyclic graph to be able to find topological sort. So how we do this is, you can use DFS to go to each node like depth wise in DFS. So you can go depth wise to all of the possible nodes that you can go to from in one path. And when you are recursively coming back, so when you are backtracking, you will just push it in a stack. You will push that node in a stack when you are backtracking. And why that works? Because since you, again, let me show it to you using paint. So since, for example, let me show you from like the simplest example. You have this, you have this, you have this. Let us say you have this 4, you have this 5, you have this 3, for example, right? So for what can be a valid topological sort for this? Let us use a stack for this. So you will go to 0, then you will go to its neighbor 1, then you will go to its neighbor 2, then you can either go to 4 or 3. Let us start with 3. You can also start with 4. So we go to 3, then we recurse back, right? So we will be adding 3 in the stack. Let me make the stack properly. So you can add 3 in the stack, right? Then you recursively come back, you go to 2, and then you go to 4, then you can go to 5, and then you can backtrack from 5. So you can put 5 in this, then you will backtrack from 4, you will put 4 in this, then you will backtrack from 2, you will put 2 in this, you will be backtracking from 1. Actually, let me just show them, like, then we can backtrack from 1, and we will have 1, we can backtrack from 0, and we will have 0. So what do we have here? If we look from top to bottom, we have a valid topological sort. And why is that? Because we have 1, 0, 1, 2, 4, 5, and 3. Now let us check if each parent node is coming before its neighboring node, or you can say child node, whatever you want to call it. So for example, 0 is coming before 1, 2, 4, 5, 3, all of these nodes, right? And mainly we have to focus on 1. So 0 is coming before 1. 1 is coming before 2. and then we can go to 4. So 4 and 2 is before 4, right? 2 is before 4 and 4 is before 5. So it is completely valid till now. And then we can go back to 3. Now, since 2 is before 3, 3 should be after 2. Now, since 3 is not related to 4 or 5, 3 can also come here and 3 can also come here. So there can be two possible valid topological sorts in this. So this is a valid topological sort. We can see it satisfies all of the conditions of topological sorting. So this can be a valid topological sort. Another can be 0, 1, 2, 3, 4, 5. This can also be a valid topological sort. So there we have topological sorts, and now I will explain the code to you. So what I'm doing is, first of all, I'm creating my own adjacency list using a map. Then I'm creating the stack in which I'm going to be pushing while backtracking, and obviously a visited vector. Then we can start visiting all of the vectors using DFS. And what we do in DFS is, obviously you mark a node as visited, you go to all of its neighbor. If the neighbor is not visited, you call DFS on that. But when you backtrack from this, you will just be pushing into U. You will just be pushing this node U, which is your current node, into the stack, right? So when you backtrack, you push into the stack. And after coming out of this for loop, basically once we have processed all of the possible nodes, we will have a valid topological sort in the stack from top to bottom. So what we can do is we can start popping elements from top and adding them to a result vector. So that is what I'm doing here, and then I can just return the result. So I have tested out this code. This works completely fine, runs and gets submitted as well. So this is the way how we can find a valid topological sort in a directed acyclic graph using DFS. And yeah, so this passes. Now I will just move on to the next problem. Okay, so now my next problem was to solve the same topological sort, but this time using BFS approach. Now for BFS, we use something called Khan's algorithm, or Khan's, whatever you want to call it. I will explain the algo in a bit, but first I would like to explain why your normal BFS would not work. So why do you use BFS? You use BFS for level order traversal, right? So you can traverse the whole graph level wise. But why that approach would not work? Let me show that to you. So for example, we have this, right? You usually keep a queue with yourself, and what you would do is you would first push this 0 in the queue, then you will pop this out, you will push 1 and 2, you will pop, just a second, you will pop 1 out, you will be pushing 3, you will pop 2 out, you will be pushing 5, right? So that is basically the way it would work. So why can we not use level order traversal to find the topological sort? So for example, let me just take a very small example. Let me just first explain it to you using something like this. For example, if we were to use level order traversal, the first element was going to be 0 in the topological sort. Then we will move on to 1 and 2, so you will be able to put 1 and 2. This level is finished. Now we will be able to move on to 3. Now this level is finished. So why is it that this algorithm would not actually work, right? So I can show it to you using this. So what is the first level? First level is 0, right? Second. So what will be the topological sort? Let me call it TS. The first level is going to be 0. We will be putting 0 in this. Then 1 and 2. We will be putting 1 and 2 in this. Then we have two possibilities. Either we first put 3 and then we put 5, right? Depending on what we had in the queue first, 2 or 1. So either we can push 3 before, then 5, and then this would work. This is a valid topological sort, right? But let me explain first why this is a valid topological sort. So first of all, 3 comes before 5. As we can see, 3 should come before 5, 2 comes before 5, 2 comes before 5, and just a second, let me clear out this bottom part. Yeah, and 5 comes before 4, 3 comes before 4. So valid topological sort. How this is valid is you can go 0 to 1, you can go 0 to 2, you can go 1 to 3, you can go 2 to 5, you can go 3 to 5, and you can go 5 to 4, you can go 3 to 4. So as we can see, this is a valid topological sort. But what if after 1 and 2, 5 was pushed in first, right? For this specific case. So if we put 5 first, then we will have something like 3 level wise, and then we will have 4, right? And you can see in this there is no cycle. You can go 0 to 1 to 3, then 5, you will have to move ahead. 0 to 2 to 5, you will have to move ahead. You can't go back. Similarly, from 4, you can't go back. So there is no cycle in this. So why this logic fails is because, let me show it to you like this. We can go 0 to 2, we can go 2 to 5, we can go 1 to 3, and we can go 3 to 5. Wait, what is happening here? Now this clearly fails, right? You can go 5 to 4, 3 to 4. But this right here, this one, 3 to 5, this 3 to 5, this clearly fails because 3 should appear before 5, right? So our normal level order traversal fails in this. So for this purpose, we are going to be using Kahn's algorithm, and I will explain how it works using my code. So what we do in Kahn's algorithm is we keep a track of the in-order degree of each node. So the in-order degree is how many nodes are incoming to the current node, or how many arrows are pointed towards the current node. For example, 0 has 3 arrows pointed towards it, right? So 0 will have an in degree of 3. Similarly, 1 does not have any arrow pointed towards it. Its in degree is going to be 0. Similarly, with 3, the in degree is going to be 0. With 2, the in degree is going to be 0. So why we are keeping a track of this in degree is so that we can use normal BFS, and whenever the in degree becomes 0, that means there is no other node pointing towards that node currently, right? So if the in degree becomes 0 for a node, then we know that there is no other node pointing towards it. So all of the nodes that have been before it have already been processed and have been pushed into the answer. So we can push the current node inside the answer, and the topological sort that way would be valid. So that is basically what we are doing. So let me explain it to you. First, I'm creating obviously the adjacency list. Then I create a vector called in degree this time instead of visited, and this in degree is storing in degrees of all of the elements, right? So then we create a queue and we push all of the elements with in degree of 0 inside the queue. Then we run a while loop until the queue is empty, and whenever we pop the front node, it is going to be an empty or a node with an in degree of 0. So since it is a node with in degree of 0, we can push it to the result, and the topological sort will stay valid. So that is what we are doing. Whenever we pop from the front, we push it to result. Then we check for all of the neighbors of the front node, and since the front node has already been processed, that node is not pointing towards any node right now, right? So we can delete that node, you can basically say, in that sense. So the in degree of its neighbor are going to decrease by 1, right? Since for example we have 1 pointing towards 0, if 1 is processed, we can remove 1, and then there will only be 2 nodes pointing towards 3, right? Because 1 does not exist in it anymore. So that is basically what we do. So we check for each neighbor of this node with an in degree of 0, and we decrease the in degree of those nodes by 1, and if the in degree becomes equals to 0, we just push it to the queue, and then the while loop continues, and then we can just print the result. So this solution works completely fine. I have compiled it, run it, and tested it out. I am able to submit it. So just remember that when finding topological sort of a DAG using BFS, you will be using an in degree array, and based on that you will be putting it in topological sort. With a DFS you will be using a stack. So as we can see, this BFS solution works completely fine. Now I will just move on to the next problem. Okay, so I just solved my next problem, and it was to check if there is a cycle in a directed graph or not. Now, in topological sort, we have already learned that a valid topological sort for any graph can only exist if it is a directed acyclic graph. And if it is not acyclic, then the topological sort is not going to be valid, right? So we can basically use that, and using that and Kahn's algorithm, or basically using the BFS approach to find topological sort, we can check if there is a cycle in it or not. So the code is same, exactly same code as I have shown you previously. The only change is that we are not appending the answer in an answer vector now. Instead of that, we are keeping a count, and this count is basically checking how many elements we have in the topological sort. So in a valid topological sort, we know that the number of elements in linear ordering is always going to be equal to the number of nodes, right, or the number of vertices. But if it is not equal to the number of vertices, then there is some kind of an error, right? And so basically that can only happen when there is a cycle. And so we will basically use topological sort in this and keep a count of how many elements are in linear ordering of topological sort. And if the count becomes if the count is not equals to the number of nodes, then we know that there is a cycle present. Otherwise, we can just return false, as I've shown right here, right? And whenever you pop from the queue, you will just do count plus plus. So let me run this and show you. So the output works completely fine. The code is simple, obviously. This is the previous code that I used, and it gets submitted correctly. Yeah, so this works completely fine, and that is how we can find if there is a cycle in a directed graph or not using BFS. In DFS, we were using a DFS visited node, right? You are just basically using the DFS visited and checking if it was present or not, but with a queue or with BFS we cannot do that. So, and level order traversal would not work, as I have already shown you previously in the previous example why it would not work, and in case of a cycle obviously it would not work. So yeah, so basically this is the solution. Now we can move on to the next problem. Okay, so I have solved the next problem as well. This one was quite simple. In this, we had to find the shortest path in undirected graph. So when it says shortest path, so each of the edges, they have a value of 1. So the weight of the edges is 1 for each of the edge. So what we wanted to do in this is we just needed to find the shortest path from the source vertex to all vertices, and that shortest path is the sum of the edges that it takes, or is the sum of the weights of the edges that it takes. So for example, if we start from 0, we want to go to 1, it will be 1, as we can see, only 1. And then for index 2, it will be 0, 1 and 2, so as the sum of both the edges, which is 2. Similarly with 3 can be reached directly from 0, so it is going to be 1, and that is the way we do for all of the elements. And if it is not, so if the node is unreachable from the source, then we are just going to be putting -1 for it. And so this problem is quite simple. I used BFS to solve it. What I did is I created a queue and I created a result vector and initialized all the values with -1, and I created visited, obviously, which is always needed, and the visited of source is going to become true after that. And then what I did is I updated the result of source by 1. So it was initially -1, right? So it would become 0, the source, and the source is added to the queue as well. Then we run a while loop until the queue is empty. We pop the front, which is going to be the source itself, and then we iterate all of its neighbor. If the neighbor is not visited, we visit it, we mark it as visited, we push it to the queue, and we update the result as the result of the previous node, basically the adjacent neighboring node, +1. So whatever is going to be the this is kind of like a dynamic approach, you can say. So whatever is the sum that we get till the previous node, there can only be one edge between the current node and previous node, which is going to be 1, so we are just going to add 1 to it, and then we can just directly return the result. So this was basically like an unweighted graph, you can say, and this solution is very simple. It works as well. I can compile and run, I can submit it. So before submitting it, let me show you one thing as well, why this condition work. Result of neighbor equals to result of front node plus 1. This front node is the parent node, you can say. So I think I should call it parent over here. Just a second, to make things easier for you to understand. Parent node, right? Let me call this parent node. Call this parent node, right? Let's see if it still works. Yeah, so the answer is correct. So what we see from this is basically whatever is the shortest part till the parent node, we are going to be adding 1 to it for the current neighboring node, and that is the way we solve it. I can also submit it, and this works completely fine. As we can see, it passes all of the test cases correctly. So now this is the case where we need the shortest path, or basically the shortest distance, you can kind of call it, for the source node till all of the nodes. So that is why we solved it like this. But if you need the actual path, for example, if we have a source node and a destination node, for example 0 is the source node and 2 is the destination node, in that, and we have to print the path, the literal path. So for example, we will go first to 0, then 1, then 2. So we have to print 0, 1, 2. What do you do in that case? So in that case, we are just going to create a parent vector instead of a result vector, and in the parent vector we are going to be storing the parent of each of the node, and using that parent at the end, we can iterate backwards using the parent. So basically we can see the parent of each node and add that to the result. So for example, the parent of 2 is going to be 1, we will first add 2, then we will add 1, then the parent of 1 is going to be 0, we will add 0, and we will have the path which is 0, 1 and 2. So if you have a question like that, you can solve it like that, but in my case I just needed like the shortest distance basically. So yeah, that was the solution. Now I will just move on to the next problem. You can also try it out with me if you want to. By the way, I think this solution should work completely fine with DFS as well. You know what, after this I will try it with DFS as well to see if it works same or not. So that is the next problem I'm going to be solving. So I have just solved this problem using DFS instead of BFS. Now I will first explain the solution to you, and then I would explain why it doesn't work. Although it does kind of work, but I will explain to you anyways. So as we know how normal DFS works, you would be iterating depth-wise. So nodes one by one, you will be going like this, basically that way. And what you want to do in this is you want to backtrack. So whenever you backtrack, you want to mark that node as unvisited. Only then you will be able to find like a new path to it, and when you find a new path to that node, then you will be able to update the result. So you have to include a new variable called distance. This time we can't update from the result of the parent because we are not traversing level wise, so we can't do that. The result would not work. What you have to do in this case is just create a distance variable, and using that you can just take distance of +1 each time. Now when you will be updating it is you will be checking if the neighbor is -1 or if the current result that we have for the neighbor is greater than distance +1, because we want to find the most minimum distance. So in both of these cases you are going to be updating the distance, and you are going to be calling DFS on it again. So when you backtrack, you will be marking it as false, so that when you come from another path you will be able to include it and check the new distance if it is possible. So that is the way it works. Now the problem with this solution is this is since you are backtracking and marking each node as node visited whenever you backtrack, so you will be going through that path again and again, and for all the v vertices you can go through that path v times, right? So the normal time complexity of DFS is going to be O of v plus e, right? Just a second, let me show you using paint, obviously the best tool for showing anything. So yeah, I hope my screen is visible. So the normal time complexity for DFS is going to be O of v plus e, but as I said, since we are backtracking and marking it as unvisited, for each node v, if there are like n nodes around it, then you can come to it n different times, right? You can visit it n different times. So you can say if there are v nodes, you can visit it v different times, right? So each one. So the time complexity for this is going to become O of v times v plus e, right? So this basically becomes O of v square plus ve, and now in the worst case, e can also become equals to v, right? In the worst case, this e right here, this can also becomes equals to v. So the time complexity for this is going to be v square. So this solution would not work because the time complexity is too high. I can show you, I can compile and run. It will run on the first test case completely fine. But yeah, when I run it for all the other test cases, it will be running for most of them. But there is going to be a test case for which it is going to be exceeding the time limit, because the time complexity now is O v square. Yeah, as you can see. So it doesn't matter what kind of solution you use using DFS to find the shortest path, it will always be exceeding the time complexity. So, but I hope, just a second, I forgot to show you the screen. So yeah, let me show it to you. I can compile and run this, and yeah, this gets submitted, the output is correct. I can also try submitting it, and it will run for most of the test cases, but for one or two test cases it is going to exceed the time limit. As you can see, it runs for most of the test cases, but for the last couple of test cases it exceeds the time limit. And that is going to be happening with DFS. If you use DFS to find the shortest path, there is no way to improve the time complexity with DFS to find the shortest path in an undirected graph. So I just wanted to show it to you. So now we know why DFS is not favorably used to find the shortest path in an undirected graph, and why we need to use BFS. So now I will just move on to the next problem. Alright, so I have solved the next problem as well. In this problem we had to find the shortest path in a directed acyclic graph. So what I did for this is, first of all, I will simply be explaining what is the solution. So we already know how to find like the topological sort, right? And we know how to save that in a stack using DFS, of course, unless you want to be using like Khan's algorithm, but you know how to find topological sort using DFS. Hopefully I have made a video on that, but and we know how to store it in a stack, like the topological sort, and the linear ordering is from top to bottom, right? So basically top is the starting of the linear ordering and bottom is the last element, you can say. So what we do after that is we can create a distance array, just like I've created it in my code, and I've called it result in this case. You can call it distance if you want to, and I've initialized it with -1 because of the requirement of the question, but I will be explaining it to you using infinity. Basically I will be explaining the code, explaining the logic of this problem to you using infinity instead of -1. So I think first we should move on to something like paint. I'm not dreaming. So just a second. So I hope my paint screen is visible. So let us take any kind of graph. We'll be starting from 0. A directed acyclic graph, by the way. So any kind of directed acyclic graph. You can say 2, you can go to 3, you can go to 4, go to 5, right? Let us take something like this, and yeah, so this should work. So first step of the solution is to find the topological sort, right? So let us find the topological sort first for this using the DFS algo. Let me create a stack right here, and yeah. So we will first go to 0. From 0 we can go to 1. From 1 we can go to 2 or 3. For now, let us say we go to 2 first. Right, let me show it to you like this. From 2 we can go to 3 or 5. Let us say we go to 5, right? We can backtrack from 5. When we backtrack, we can just add this directly and mark it as visited. So this is already visited, right? So we backtrack to 2, then we can move on to 3, and from 3 we can go to either 4 or 5. 5 is already added, so we won't be going to that, it is already visited. Then we go to 4, and we backtrack from 4, we will mark it as visited, and 4 is added. Then we go back to 3, from 3 we cannot go anywhere else, so we will mark it as visited and recurs back. Now we go to 2, from 2 we cannot go anywhere else, so we have already explored all the options, so we will mark it as visited. This is 2, and then we will mark 1 as visited. Now we can finally mark 0 as visited, right? So let us say we want to find the shortest path from 1 to all the nodes, right? So let us say this 1 is the source. So from 1 we want to find the shortest path to all the nodes, and right now we have the topological sort stored in a stack, right? So what do we do now? What we can do, also let me like write some values in this. For example, 5 is 2, we can call this -1, this is 3, this can be 4, this can be -2, this can be 5, right? So I basically gave weights to each of the edge. I think I should turn off my color thing right now. Let me make them red for now. So first is 5, the weight is 5, the weight of this edge is 2, the weight of this edge is going to be -1, the weight of this edge is going to be 3, weight of this edge is going to be 5, weight of this edge is going to be 4, and this one is going to be -2. Another one is left, let us put this as 1, why not, right? So now we have all of the nodes, right? And we want to find the shortest path from source to all the nodes. So let us start by finding the shortest path. Let us say 0, 1, 2, 3, 4 and 5. Now from 1 we cannot go to 0, so its distance is going to be infinity. From 1 to 3, from 1 to 2, there is only one way from 1 to 2, so we will put it -1, and 1 itself is going to be 0, of course. And then from 1 to 3 there are two ways, -1 plus 3 or 2. Now both are equal, so the minimum distance is going to be 2 in this case for 3, right? Let me write it like this. Nodes distance, let me say minimum distance, right? So till 3 we can have 2. Now we have done 0, 1, 2, 3, right? Now we can move on to 4. Now there is only one way to go to 4, right? And that way is to go from 3 to 4, and the minimum distance towards 3 is 2, no matter what you do. So we will say 2 plus 4, which is 6. Now 5, we have multiple ways of going to 5, right? We can go to 5 from 2, we can go to 5 from 3, and we can go to 5 from 4, right? Now if we go to 5 from 2, and the minimum distance for 2 is -1, so it will be -1 plus 5, it is going to be 4, right? So, and if we go from 3, the distance for 3 is 2, and then it is going to be minus 2 from 3 to 5. So the minimum distance is going to be 0, which is less than 4. So right now the minimum distance till 5 is going to be 4, is going to be 0, I mean. And then from 4 we can go to 5. It is going to be 6 plus 1, which is 7, which is already too high. So the minimum distance toward 5 is going to be 0. Now this is what we found by basically running it intuitively, right? So what do we do now? What we can do to solve this problem is we already have the topological sort. Let us call this topo sort. We already have the topological sort. So what we can do is we can create a distance vector, right? This can be our distance vector. We can have 0, 1, 2, 3, 4 and 5, right? Now we can initialize distance towards all of the nodes with infinity, right? In my code specifically that I submitted on Geeks for Geeks, it is -1, but that is according to the requirement of the problem itself. I am going to be explaining it to you using infinity for better understanding. So why is each one initialized to infinity? Because initially we cannot reach any of the nodes, right? So what we are going to do is we are going to be putting the distance of the source node towards itself as 0. Currently it is infinity, we are going to put it to 0, and source node is 1, right? Then what we do is we pop from the stack, and when we pop from the stack we check if the distance is not infinity, right? Because if the distance is infinity, then that node can never be reached, right? That node can never currently be reached, you can say. So since that node can never currently be reached, its distance is going to be infinity when we pop it from the stack, and if its distance is infinity, then obviously since we cannot reach that node, we cannot reach any other node from it either, right? So we are going to be skipping it, and whenever we hit a node whose distance is not infinity, then we are going to process it. So for example, first we are going to pop 0. The distance of 0 is infinity, so we are going to ignore it. Then we are going to pop 1. Distance of 1 is 0, so we are going to process it. Now what we are going to do with 1 is we are going to be checking all of the neighboring nodes of 1, right? So there are 2 neighboring nodes of 1, which is 2 and 3. And so for 2 and 3 we are going to be checking their distances. So since the distance to reach 1 is 0 itself, so to reach 2 it is going to be 0 plus -1, which is going to be -1. So we are going to be updating it to -1, right? Because it is less than infinity, or less than the current distance that this node have, right? So the current distance for 2 is going to be becoming -1. Similarly with 3. Now with 3 we are going to be checking if the current distance is less than what 3's current distance is. So it is going to be 0 plus 2, which is less than infinity, which is 2. So we are going to be updating it to 2. Then we will process 2, for example. Then we will pop from the stack again. This time we have 2. 2's distance is not infinity, right? So we are going to process it. Now from 2 we can go to 5 and 3. So let us go to 3 first. So the distance till 2 is -1. So we are going to be doing -1 plus 3, which is going to be 2. Since the distance of 3 is already 2, we have no need to update it because it is not less than the current distance of 3. Then we will process for 5. So we have -1 plus 5, right? -1 plus 5 is 4, and 4 is less than the current distance of 5, which is infinity. So we are going to be updating it to 4, right? Then we have processed all of the nodes from 2. Then we are going to pop the next one, which is 3. The current distance till 3 is 2. It is not infinity, so we are going to process it. And 3 has 2 neighboring nodes, which is 4 and 5. So we are going to first check for 4. The current distance till 3 is 2, so 2 plus 4 is going to be 6, which is less than the current distance of 4, which is infinity. So we are going to be updating it to 6, right? Then the next one is 5. Current distance till 3 is 2. Now 2 plus -2 is going to be 0, and current distance of 5 is 4, which is less than which is greater than 0, right? So the new distance that we have found is less than the current distance that 5 already have, so we are going to be updating it to 0. Now we are going to be popping 4. From 4 we can see that we can only go to 5, and distance till 4 is 6, so 6 plus 1 is going to be 7. So 7 is not less than the current distance of 5, so we are not going to be updating it. Finally we will process 5. Now 5 is going to be, since it does not point to any node, we are not going to process, so it must, we are not going to be making any changes. And that, now we have this answer basically, which is infinity, 0, -1, 2, 6 and 0. Now is this similar to the one above? We have infinity, 0, -1, 2, 6, 0, infinity, 0, -1, 2, 6, 0. So yeah, so this algorithm works. So what you have to remember in this is, when you're finding the shortest path in a directed acyclic graph, always remember, in a directed acyclic graph, I've come to notice a pattern that most of the problems can actually be solved using the topological sort, right? For a directed acyclic graph. So I think the first thing that should come to your mind whenever you hear a directed acyclic graph is a topological sort. So in this specific problem, when we have to find the shortest path from the source node to all the nodes, so first we are going to be finding the topological sort, and then we are going to be creating a distance array, and then we are going to be putting the distance of the source to 0, because obviously the source can reach itself with a distance of 0. So then we are going to be popping from the stack itself, and we are going to be checking if the current node has been visited or not. If it has not been visited, its distance is going to be infinity, which means since it has not already been visited, we cannot visit other nodes from it. So we are just going to skip in that case. Otherwise, if the distance is not infinity, that means we can process that node and we can reach other nodes from that node. So we are going to be processing its neighbor, and we are going to be calculating the new distance. If the new distance is less than the current distance of the node, then we are going to be updating it as the minimum distance. Otherwise we just move on, and then we could continuously keep popping from the stack and checking these conditions. That is it. So I'm again going to make my screen black and white. Now yeah, so now let me show you the solution. So I'm sorry, I have a cough, a cold, you can say, kind of. So the first is going to be the first process that we have to do. Obviously I created my own adjacency list, and this time in the adjacency list I am adding a vector of pair instead of just a vector itself, because we also have the weights for each of the edges. So we are going to be storing the node itself and the weight, right? Let me write it here. Pair in comma int is node comma weight, right? So, and then we create the visited vector, obviously always used. Then we create the stack, and then we can start iterating all of the nodes and calculating, calling DFS on it. In the DFS, obviously we run normal DFS, and when we backtrack, we push the current node to the stack, right? Now what we have to do after finding this topological sort, which is stored in the stack, we have to find the shortest path, right? So I of course created a result vector called result. You can also call it distance if you want to, because it is going to be storing the minimum distance from current node till each node. And I'm initializing it with -1 because the problem tells me to return -1 is in case the node is not reachable from the source. So instead of infinity, it is -1 in this case. Then I call the helper function that I created. Now in this case the source is always going to be 0. It is mentioned in the problem. We have to find the shortest path from source 0 vector to vertex to all vertices, right? So then I call this shortest path helper. We have the source, which is going to be 0 always. I pass in the adjacency list the distance vector or the result vector itself and the stack. Then obviously the first step is to put the distance of the source itself to 0, right? Then I start processing until the stack itself is empty. First of all, we are going to be popping the topmost node, and then we will just check if the result is -1 or not. If it is -1, that means that node has not been reached yet. If it has not been reached, that means we cannot process it. or basically we cannot reach other nodes from this node, so we are going to be continuing in that case. Otherwise, if that node has been reached and its distance is not equal to -1, then we are going to be visiting all of the neighbors of this node. And I have just created two variables called the neighbor node and edge weight for better understanding of you guys. So the neighbor node is the neighboring node, and the edge weight is the weight of the edge connecting the current node and that neighboring node. So I'm just going to check if the result of neighboring node is equal to -1, or if the result of the top node, or basically the distance of the top node plus the edge weight, is less than the current result of neighbor node or node. So basically, if it is -1, then in that case it is that node has not been reached yet. Then we can just directly update it. Otherwise, we can just check if the distance is the new distance that we get, which is the distance till the current node plus the weight of the edge connecting its neighbor, is less than the current distance that it is taking to reach the neighboring node. If it is less than the current distance for the neighboring node, then we are going to be updating the neighboring node. Only in two cases we updated. Either it is -1, basically it has not been reached yet, or the new distance that we find is less than the current distance that we have for the neighboring node. And then after coming out of this loop, we can just directly return the result. So the solution works completely fine. I have run it, I have checked it. As you can see, the output is correct. I can also submit it. So this was the solution for this problem. I hope I was able to explain it well enough. If I'm not, you can go and online and check out other people's solution as well. For now, I'm just going to move on to the next problem. Okay, so I have just solved the next problem. The next problem is just simple Dijkstra's algorithm that I've applied, so you can skip this one if you want to. But I will be explaining the code here, and in the end I will also be explaining one more thing, so you can stay for that if you want to. So first of all, if Dijkstra algorithm is to basically find the shortest path in a weighted graph, it can either be directed or undirected, and it can only work in graphs that don't contain any negative weight edges. Now I will be explaining that in the end why it is like that, but first I will be explaining the solution. So by the way, this is just simple Dijkstra's algorithm. If you want, you can just skip this and watch somebody else's solution online, because obviously the algorithm itself is going to be same everywhere. Just internally what kind of data structure you are using is going to be a bit different. So in my case, I'm going to be using a set, and I will explain the solution based on that. So this is an undirected graph. It can be directed, doesn't matter. So we are given an edges vector, and this vector has the edges u comma v and their weights, so the weight in between as well. So 0, 2 and 6, basically like that. So I basically created my own adjacency list using this, and then I created a distance vector, and I initialized all of its values with the maximum possible value, which is int max. Then we obviously put the distance of the source at 0, and then we create a set st. Now why we are creating a set? Because each time we are going to be popping out the node which has the minimum current distance. Now so we are going to be inserting first of all 0 comma that source inside this set. Then obviously we will run a while loop until this set is empty. We are going to be checking if we are going to be first checking the minimum element in the set, which is going to be the first element at the beginning, because the elements are ordered in a set. So we get that first element like this, and then we erase that element from the set because we have got that element. We are going to be popping it. Now we are going to be iterating the neighbors of that set, and for each time we are just going to check if the distance of the current node that we have, so this is that distance that we got from the set. So this minimum distance that we currently have plus the weight of this neighbor node. So basically the weight of this neighbor node plus the minimum distance that we currently have. If it is less than the distance that we have in our distance vector for this neighbor node, then in that case what we are going to do, we are first of all going to check if that node is already present, this neighbor node is already present in the set or not, because if it is already present, then in that case we are going to have to pop it first. So we just find it like this. Now if we already have it in the set, we are going to have this distance as well, and this distance is going to be the distance that we have updated in the distance vector, or the distance that we have in the distance vector for this neighboring node. So if it is already present, then we are going to erase it, and then what we are going to do is we are going to be updating the distance in this distance vector like this. So basically distance node dot first plus the weight of the edge, right? So minimum distance that we have and the weight of the edge, and then we are going to be inserting this in the set as well, and then we run this while loop until it is empty. In the end we can just return the distance itself. So this is just simple Dijkstra's algorithm, and the solution works completely fine. I've tried it out, I've submitted it, and it works completely fine. Now I will first be telling you the time complexity, and then I will tell you why it doesn't work for negative edges. So I'm sorry, again I have a cold. So yeah, this works. Now the time complexities for this is going to be basically O of just a second, I will tell you that in Paint quickly. Yeah, so the time complexity is going to be O of V plus E times log V. Now why is that? So this is because we obviously already have V plus E time complexity, because we usually iterate all of V vertices and E edges, right? So V plus E comes from there, and the log V comes from the set. Now in the set we can have at most V vertices because it is a set of vertices, and the time to insert, find and delete an element from the set is it takes about log of V time. So that is the simplest explanation that I can give you for that. So for each edge we can insert, delete or find this set, which is going to be log of V. So that is the time complexity for this. And in usual cases, in a corrected graph, the value of E or the number of edges is greater than equal to vertices minus 1. So if we want, we can just like neglect V log V. In that case the time complexity is going to be E log V. So usually you will be seeing this as a time complexity. People will tell you the time complexity is E log V, but where this E log V comes from, now you know. It is because the original time complexity is V plus E log V, and since in a corrected graph the number of edges is greater than equal to V minus E, so we can neglect V log V if needed, and this is going to be the final time complexity. And yeah, so the space complexity can be V or V plus E, you can say, kind of, because we are storing the elements in the set and we are using a distance vector which is of size V. So that is basically it. Now I will be explaining why negative edges don't work. So I will be using this case to explain that. This one right here, right? I will be using this to explain why it doesn't work. So what Dijkstra's algorithm does it is basically a greedy approach, you can kind of say. So it is a greedy approach, and each time it is finding the most minimum distance to a node, right? And it is assuming that in the future we cannot find a distance which is more minimum than the current distance that we have for that particular node. So if we have negative edges, that assumption is violated. And why? That is because for example, we start with a distance for A. Let me create the stack. Now if we start with A, the distance for A is going to be 0. So you can say 0 comma A in this, right? Now we pop A, and then we are going to be now since we are going to be popping the most minimum element from the set, sorry, not a stack, this is a set. Let me go right here, a set. Yeah, so we are going to be popping the most minimum element from this, which is 0 comma A in this case, or minimum, basically the one with the most minimum distance, which is 0 comma A. And then we are going to be checking the distances for both of its neighboring nodes, which is B and C, right? So for each of them we are going to be adding the most minimum distance that we currently have with its vertex. So for B it is going to be 0 plus 4 comma B, and for C it is going to be 0 plus 2 comma C, right? And then we are going to be adding these. So first we are going to be adding 2 comma C, and we are going to be adding 4 comma B, right? Let me erase this. Now we are going to be popping the element with the most minimum distance. In this case it is going to be C, so you will be popping C from this. By the way, let me keep updating the distance as well. This is the distance vector that we are using. Let us say 0 1 2. In this case it is going to be A, B and C, so let me go with A, B and C, right? Create it like this. So minimum distance for A is going to be 0. For B the minimum distance is currently going to be 4, and for C it is currently going to be 2, right? Now, as we said, the Dijkstra's algorithm is a greedy algorithm. It assumes that we are not going to be finding a path which is lesser than the current path in the future, right? So when we pop 2 comma C from here, now since it doesn't have any neighboring nodes, we don't do anything. Then we pop 4 comma B, right? Because it is the most minimum one currently. And from 4 comma B we can see that if we do 4 minus 5, it is going to be equal to minus 1, right? So this should be the most minimum distance to C, minus 1, right? But since Dijkstra has already basically you can say assumed that you won't be able to find a more minimum distance basically, so this assumption is violated, and you are going to be finding a negative distance in the future, but this negative distance should not work because of the Dijkstra's greedy approach, and basically the approach that we have been using currently fails, right? So that is basically it. I hope I was able to explain it well enough, because I will be honest, even I am a little bit confused right now, but I think it works. So this should be minus 1, but it won't be because it will be putting it as 2 in this case. So that is it. And this is a directed graph. If we have a distance of negative, then it can be reversed as well, you can kind of say. So if it was not a directed graph, for example, it is undirected like this, so we have minus 5, but which direction is minus 5, right? You don't know that. So in that case it also fails, you can kind of say, because one direction is going to be minus 5, then the other should be 5, right? Otherwise both can't be minus 5. You can't be moving a distance of minus 5 in reality. So that is basically it. I hope my explanation was clear enough. Now I will just move on to the next problem. You can also search for other people's solution online and explanation of Dijkstra's algorithm. Other people might have done a better job than me. So we will just move on to the next problem now. Alright, so I have solved the next problem as well. And the next problem is nothing but a minimum spanning tree using Prim's algorithm. So it is a very common algorithm. You can go online and search for it. But I will explain my solution for it and everything that I've used basically. So first of all, you obviously create your own adjacency list however you want. This is the way I have created it, as I have been created it since the beginning. Then you create this key vector. This key vector is nothing, it is just storing the minimum distance for each node. So you can also call it dist if you want, or min dist. The choice is yours. I'm just calling it key. And then I'm using a set. Now why I'm using a set in this is because in the set I'm going to be storing the current minimum distance and that node, right? So in Prim's algorithm we have to continuously fetch the node with the current most minimum distance, right? So if you want to fetch the node with current most minimum distance, then we need a fast way to do it. Now fast way to do it is going to be either using like a priority queue or a set. I've used a set in this case, but you can also use a priority queue, and I will also explain to you how you can use a priority queue in a second. So Then we are using an MST vector. Now this MST vector is nothing but the visited vector that we have been using till now. In this case it is called MST because we are using this to check if a node is already part of MST or not. This is obviously just used so that we do not process nodes again and again and get stuck in an infinite loop. And then we have the parent node. Now the parent node in this specific problem is not needed. Why that is because in this case we only need to print out what is the sum of weights of the minimum spanning tree, right? The sum of weights of the edges in the minimum spanning tree. We just have to print that. So we don't exactly need the parent, but you need the parent vector in case you have to like return which all nodes are connected with which node and stuff like that. So that is why we are using it. You can also avoid it if you want to in this specific question. But anyways, so then initially we are putting the minimum distance for each of the node as the most maximum distance possible using int max. Then we put the distance of the starting node. In this case the starting node we are going to be putting it as 0. So we are going to be putting its distance as 0. And then we are going to insert it into the set. And we are going to be inserting it as min distance comma node. So min distance comma node because we want to get the minimum distance, so ordering should be based on minimum distance rather than the node. So that is the reason why we are doing it. And then you can iterate for all the nodes v, you starting from the first node, because the 0th node we have already processed, so you will be starting from the first node, right? In a minimum spanning tree, if you have like v nodes, then the number of edges that you are going to have is v minus 1, while also keeping the sum of these edges as minimum as possible. So that is basically a minimum spanning tree. So that is why we are starting from index 1, because we need v minus 1 edges, right? And there are v nodes. So first of all, we are going to extract the beginning of the stack, which is going to be the most minimum distance node. Currently we are going to erase it from the stack, and then we are going to update MST of u. So basically we are going to mark it as visited or as being part of the minimum spanning tree. So we will put it to true. Then we will iterate over all of its neighbors, and in the neighbors we are first going to check if MST is false or not, because if MST of that neighbor is true, that means that neighbor is already a part of the minimum spanning tree. Then we can avoid processing it. Otherwise, if it is not already a part of minimum spanning tree, then what we can do is we can check if the current weight is less than the current distance that we have for that node, right? So the current distance that we have for that node is probably going to be infinity, right? And if it is not infinity, that means it has not been made a permanent part of if it is not infinity, and if its MST is still false, so it means it has not been made a permanent part of the minimum spanning tree, because we have not marked it as true yet. So basically we have not found the most minimum one possible for it yet, as we know that we are extracting the most minimum distance node each time from the set and marking it as visited. So we have not found it. We have not found its most minimum distance yet, or the most minimum edge, you can say, kind of. So what you are going to do, you are going to check if the weight is less than its current weight, or the current distance, you can call it whatever. Current weight is the right term in this case. So if it is less than the current weight, then what we are going to do is first we are going to try and find this node with its current minimum distance inside the set. If it is found, then we are going to erase it, and then what we are going to do is we are going to be updating its current distance or the current minimum weight with the current weight, and then we are going to be inserting it in the set again. Then we are going to be marking its parent as u, because we have found this minimum edge for this neighboring node when we come to it from u, right? So when u is the parent, then we have found the minimum node. So as I said, you don't exactly need the parent vector in this case, but I think it is a good practice if you're using it, so that you do not get stuck in the future. But yeah, so once you have completed this whole loop, what you will notice is in in the key, you have the most minimum edge for each of the nodes, right? So the most minimum edge to reach to each of the nodes starting from the current node. That is basically what you have. So what you are going to do now is you are going to create a result, or you can also call it a count. So you are going to create either a result or a count variable, put it equal to 0, then you're going to iterate the key, and if the distance is not infinity, so which it most probably won't be in a minimum spanning tree because everything has to be connected. So it has to be a connected graph. So it probably will never be int underscore max, but I'm just putting the condition, why not? So, and you add this value, this edge value to this result, and then you can return the result as they are asking for us. So we will have the sum of 1 and 3, which is 1 plus 3 in this result basically. And this solution works completely fine. I have tested it out. It's a bit confusing, the algorithm itself, the Prim's algorithm is a bit confusing, I would say, but once you understand it, it is quite intuitive, I would say, and fun if you were to ask me. Like, I think it is a great algo if you were to ask me. One thing you need to make sure of this, just always remember that you have to use some kind of a data structure so that you can extract the most minimum distance node, right? And in this case, you are not going to be updating the distance, you are just going to be updating the weight. That is all you need. Instead of the distance, which is basically the sum of the distance of current node plus this weight, you are just going to be checking this weight with the current key. That is it. That is all you have to do. And obviously make sure to update it with the new distance in the set. And I can also submit this code. This works completely fine. I have tested it out. As we can see, the number of test cases is quite low for this, which is 71. Why that is because the Prim's algorithm can be O of V square, although mine over here is O of N log N or V log V, you can say whatever, but it can be N square or V square, you can kind of say, because if, for example, I was not using this set, then I would have to iterate this key each time to find the most minimum one, and it would become V square because there are a total of V nodes, right? But since we are using this set, now we can find the most minimum node in O of constant time, which is O of 1, it is always going to be the first one. But sorry about that. But inserting and finding and updating the value in this is going to be log n, right? So the overall solution will become O of log n. O of V log V, you can kind of say, right? Because there can be a total of V number of nodes in the set, so it's going to be O of V log V. That is it. That is the solution for this problem, you can say. And now I will explain to you how to do this using priority queue as well. So with the set we can use the find function, but with a priority queue we cannot use the find function. So what you can do, instead of erasing from the priority queue like this, you can just put the new distance comma that node inside the priority queue, and when you are popping from it, right over here, when you are popping the most minimum one, which is going to be the top of the priority queue, you will just check if the minimum distance is equal to the minimum distance stored in the key for that node. So I think I should just show it to you how to do it. Let me quickly do it. Hopefully it would work. So we have a pair in this priority queue, which is going to be int comma int, and we can call this pq. Now we also need a data structure in this, so it is going to be pair of comma int, and we need greater pair int comma int so that it stores the most minimum node at the top. Now once we have that, we can do pq dot push. I will also explain to you why I would not prefer this solution, why I would prefer a set solution in a second. So if it is already present, so we are going to be extracting it like this, pq dot top, right? And we are going to be doing pq dot pop. basically, right? And instead of erasing it like this, what we can do now is we can check if the minimum distance of this node is equal to the current one or not. Because if it is not, for example, if key of u is not equals to the current minimum distance that we have, which is going to be mini pair dot first, right? If they are not equal, then we know that it is outdated. It is an outdated one because it is greater. Then in that case, we can just continue. Simple as that. And now we don't need all of this. We basically, there is nothing else to update here. And in this, we can do pq dot push. Now let's see if this works or not. Hopefully it would work. Hopefully. I am not sure. Okay, this works. This works completely fine. So as I said, you can just do an outdated check. Okay, the output is wrong. So I might have made a mistake somewhere. Input is too large. Oh, sorry, that is just for the download file. I'm just getting the wrong output in this. So just a second, let me check why it is wrong. Okay, so I think I kind of understand what might be going wrong. Since I'm calling this loop v minus 1 times exactly, and since we are pushing outdated entries in PQ as well, so because of those outdated entries, it might only process like v minus 1 times, but since we are putting outdated entries, the number of nodes in it is going to be greater than v minus 1, so it won't be able to process all of them. So I think what we can do for this is we can change it for a while loop and just check if run it until PQ is not empty. This should work, I feel like. It should work. Okay, this works for this test case. Let us check now. This works. Okay, so this works completely fine. Wow. So, but I would like to avoid using it. Why that is because, as I have just said, since we are putting outdated entries in it, the size of this PQ is going to be can go greater than v minus 1, and because of that the time complexity can increase a little bit. Although overall time complexity is going to be v log v, obviously, because we are using a data structure that does everything in log v, which is the priority queue itself, but the space complexity is going to increase a little bit, obviously, and obviously it might need a few more iterations to process. So if you want, you can avoid using a priority queue and use a set, but I've told you how to use a priority queue as well. I did it so that none of us can forget. If in the future we need to use a priority queue for this, now we know that we can push in outdated entries inside of it, and we can check if the entry is outdated or not. Check if the entry is outdated, right? So that is it. Really good problem. I really enjoyed solving this. Now I will just move on to the next one quickly. Okay, so I have solved the next problem as well. In this we just had to again find the MST, but this time using Kruskal's algorithm. Now Kruskal's algorithm in itself is quite an interesting algorithm, I would say. I would suggest all of you watching this to first go online and try and understand the algorithm. Then come and watch this again if you want to. I will also explain it, but my explanation won't be in too much detail, so I will be a little bit quick about it, but yeah, proceed as you wish. Now I will just explain the algorithm first. So for the Kruskal's algorithm, it doesn't work like the normal, you can say normal Prim's algorithm that we use. What Kruskal algorithm uses is disjoint sets. So what disjoint sets are, basically two sets that do not have any common element. So you can say A intersection B is equals to phi in that case, right? So yeah, those are disjoint sets, and those are basically what it uses. So for this, what we need is we need to create some sort of a feature that can, or basically you can say we need to create disjoint sets, right? And a way to combine these disjoint sets. So we won't actually be using the sets data structure, but it is for more of an understanding. So what we are going to be using instead is a parent vector and a rank vector. And how we use it is, the parent vector is obviously used to define the parent of an element in a set, right? So whatever is going to be the parent of that element in the set is going to be its parent. And what rank defines is, since each set can only have one parent, the rank defines how many elements you have got attached to that specific parent, you can say, right? So in a set there can only be one parent, and how many childs does that parent have? And the child in that case means all of the nodes in the set except for the parent set, you can say. So basically let me explain it to you using paint, I guess that would work better. So what I was saying is that we need a parent vector. Just a second, let me quickly update. I hope my screen is visible. So we need a parent vector, obviously, right? And what we need to do is, for example, we have any element, you can say 1 right now. So we can just say this 2 is 1 is the parent of this 2, right, in the set. So, and this 1 is also the parent of 3. This one can also be the parent of 4. Now in this case you might think that the parent of 4 is 3, but that is not how we are solving it. We are calling the parent the topmost element in a set. So this is a set, you can say, and in this set the topmost element is 1, right? So there can only be one parent, and this one is the parent. So this one is also the parent of 4. And the way we are going to write this algorithm is that currently we have 1, 3 and 4, right? But in the algorithm, what the algorithm does is, instead of 1, 3 and 4, initially it will have 1, 3 then 4, but it will update it so that 4 points to this 1, right? That is the way this algorithm works. So that is a feature of the disjoint set that we are creating, like, right, to make a disjoint set and get its union. I have not come to the Kruskal's algorithm yet, but I am explaining the disjoint sets first. So this is how the disjoint set would work. Let me say parent of 2 is 1, parent of 3 is 1, parent of 4 is 1 as well. Another thing that we are going to be using is rank. Now what is rank? Rank is nothing but the number of children that a parent node has in a set, or you can say all of the elements in the set except the parent node itself. So that will be the rank of that parent node. So in this case the parent is 1, right? So the rank of this one is going to be 1, 2 and 3. In this case it is going to be 3. That is how the rank function works, right? So we need these two things, and what we need is, first of all we need to create the set. So when we create the set, we do nothing, we just create the parent and rank vector, and we initialize all of the nodes as the parent of themselves. So parent of I is going to be I, or you can also say, for example, initially if we have just these 4, 1 is parent of itself, 2 is parent of itself, 3 is parent of itself, and 4 is parent of itself, right? So you can say right now we have 4 different sets of elements, you can say, and each node is parent of itself, and we are going to be defining each of their ranks as 1. So let me write parent and let me write rank. So each node initially has a rank of 0 because they have no other nodes attached to themselves, or no other node as their children in their set. So we are only going to be having 0 in this case. Then The next part of the algorithm is the find parent function. So what we want to do is we want to be able to find the parents of all the nodes, and what I'm doing in the code is, if a node is a parent of itself, then we have found a node. How that works is, let me explain it to you. So as we can see, initially each node is a parent of itself, right? One is pointing to itself. So if in the future we, for example, change it, like 3 is going to become the parent of 4, then 1 is going to become the parent of both 3 and 4, right? Kind of like that. So what happens in this case is 1 does not have any parent, right? So 1 is going to be pointing to itself in the parent vector, and this basically tells us that the node pointing to itself, or the node which is the parent of itself, is the parent of these other nodes, for example 3, 4, 2. So that is basically what you have to understand for this. So that is the way we find the parent. Now if the parent node is equals to that node, we just return that node. What we do otherwise is what I told you we are doing with the nodes. So for example, initially we have 1, then we have 3, then we have 4. So each time you want to find the parent of 4, you will have to iterate all of this way, right? You have to iterate these two nodes all each time, and there can be multiple nodes. For example, there can be a 5 here, a 6, and it can go so on like this. So this will be too long. So what we do instead of this is, when we find the parent for this 4, for example, we are going to be going to 1. So first of all, we are going to get the parent as 3, then we are going to get the parent as 1, right? So what we are going to do, we will update the parent of this 4 from this 3 to this 1 whenever we find the parent of this node, right? So that way the algorithm will become more efficient. So that is basically what we are doing in the code. What it does is it recursively calls the code to find the parent of that node. So it will go up the tree, you can kind of say, the one that I showed you, and it will make the parent node each time equal to that node. So all of the nodes that are sequentially going, all of their parent is going to become the actual parent node itself. That is basically what will happen with this piece of code right here. So then another important piece of code is union set. So how do we combine two pieces of sets, right? So let me explain it quickly. You have two pieces of sets. For example, initially let us have something like, we have one pointing, we have like this, and we have like this. Forget about everything else I've shown you up here. For example, let me just quickly drag it below like this here. So let us have the parents in this case, the parent vector for each one. We have 1, we have 2, we have 3, and we have 4, and the ranks. So since 2 does not have any children, you can say its rank is going to be 0. Similarly with 4, the rank is going to be 0. Now the rank for 1 is going to be 1, the rank for 3 is going to be 1 again, right? So, and the parent of 1 is going to be 1, parent of 2 is going to be 1, parent of 3 is going to be 3 itself, parent of 4 is going to be 3, as we can see from these two. Now what we have here is two pieces of two sets, you can say. These two, right? Now these two are disjoint sets, S1 and S2. Now we want to combine these two. How do we combine them? We will merge them or union them based on the ranks. So how do we do that? So we just check if their ranks are equal. For example, we get 1 and 3 right now, right? We have 1 and 3, and since their ranks are equal, 1 and 1, you can assign whichever one you want to whichever one. So we can assign 3 and 4 to 1 like this, or you can also go other way around. You can also assign it to 3. 1, 2 can also go to 3, right? Now this is one way of doing it, but this is the case when their ranks are equal, right? So for example, if their ranks are different, let me have another one here. Let me have 5. In that case, the rank of 4 is going to be 1. Let me quickly edit this. Now the rank of 4 is going to be 1, and the rank of 5 is going to be 0, and the rank of 3 is going to be 2, right? 2. So just a second, let me quickly clear this part out. Yeah, so we have this new node attached, and now this is the new set. This whole thing is the set S2, right? S2. So how do you attach it now? What you have to do is you have to find the rank of the parents for these two, right? For example, we have 2 and 5 in this case. For example, we have 2 and 5, or you can also say 2 and 4, whatever you want, doesn't matter in this case. Now the rank for parent of 2 is going to be 1, which is 1. Let me say rank of parent, right? We are going to be checking the ranks of parents. Another important point that we are going to be checking the ranks of parent. Previously I wrote 1 and 3. Obviously you can use that as well, that is a way. So in that case both of their ranks were equal, but that doesn't matter anyway. So we are going to be checking the ranks of their parents, and for 5 the parent is going to be 3 and the rank is going to be 2. Now keep this in mind. The parent of 2, let me write the parent over here. The parent of 2 is 1 and the parent of 5 is 3, right? And the rank of 3 is 2. The rank of 1 is 1. So what we are going to do is, since the rank of S1 is smaller, you can say this whole set S1, the rank of this is smaller. Let me write it like this: the rank of S1 less than rank of S2, right? So we are going to be making this S1 a part of this S2. Now why we do this is, if you merge the smaller tree in the bigger tree, then your height cannot increase much, right? But if it is the other way around, if you combine the bigger tree in the smaller tree, then your height can increase quite a bit. So to avoid that, we are going to be making the one with smaller rank the part of the tree with bigger rank, or the part of the set with bigger rank. So in this case, this has a bigger rank. So, and these are the parents. So we are going to make parent of 1, which is the parent of the whole set, you can say parent of 1 equals to 3. So this 3 is going to merge with this. This 1 is going to merge with this 3. It is going to look something like this. We have a 2 coming to this. Now this goes all the way up to 3. This has a 4, and then we have a 5 right here. That is the way this whole thing works. So that is the way union set works basically, and each time you are going to be updating the parent like this. So the one with bigger rank, so the one that has smaller rank, its parent is going to become the one which has the higher rank, you can say. So this is the code. First we find the parent of both of these nodes, whatever they might be. If the parent of V is smaller than the parent of U, or the rank of the parent of V is smaller than the rank of parent of U, then you make parent of V equals to parent U, you can say, right? And then you will update the rank of U by 1. Yeah, also update the rank of this 3 by 1. So rank of this 3 is going to become plus plus. This is it basically. So initially its rank was 2. Now its rank is going to become 3, just like that, right? So that is it. That's all you have to do for this. Now let me go back to the code. Now my explanation might not be the best. This is a weird algorithm, I would say. Even I'm a little bit confused, but let me show you the union set. First we find the parent of both U and V. You can just assign them equal to U and V in this case. So let me write parent of u, parent of v. So now we just check the rank of these parents. The one with the smaller rank, the one with the higher rank is going to become the parent of the one with the smaller rank, as you can see right here. And then we update the rank of the bigger one by one. So this is basically it for that. And then we come to the main Kruskal algorithm. First of all, we create both the vectors parent and rank. We make the set as I have shown you in the make set code like this. Then you will sort it. So yeah, another thing is now we have moved on to the Kruskal's algorithm after disjoint sets. So for Kruskal's algorithm, what you are going to need is you are going to need a linear ordering of the elements, and that linear ordering will be based on the weights. So you are basically linearly ordering the elements based on the weights, and since we are starting from the minimum weight going to the maximum one, we are going to be able to find the minimum spanning tree, right? Because the overall sum of the weights that we include in the sets is going to be most minimum possible. So that is the reason you need to sort based on the weight, and the custom comparator looks like this. Since the third element or the element at second index of this edges vector is the weight, so we just do this. Make sure to make it static, otherwise this would not work. Then this is just my result. Then I iterate all of the elements in the edge, and then I find the parents of both the nodes in it, and then we just check if the parent is equal. That means both are already part of the same set. In that case, we can continue. Otherwise, we can union their sets, and then we can update the result with this weighted edge, and then you can just return this result. This code works completely fine. I have tried it out, I have tested it out, it works well. Now I can just submit it and it should work completely fine. Yeah, so this works. Obviously my explanation might not have been the best. You can check out other people's solution online and their explanations for better understanding of the algorithm itself. Now I will just move on to the next problem. Okay, so I have finally solved my next problem as well. In this we had to find a bridge edge in a graph. For that we used Tarjan's algorithm. If you want, you can go online and search for Tarjan's algorithm if you want. I will explain the algorithm first quickly and then explain my solution, and I will also be explaining something that I had been stuck on for days. So basically all the explanations online, they were using a particular word or sentence, you can say, that did not make enough sense to me in terms of the algorithm, which was making it too confusing for me. So I'll be explaining that as well. First, let me show you how we solve it. So I hope my screen is visible. First, let me tell you what a bridge edge is. So a bridge edge can be any edge that if you remove that edge, then you can basically create two components, or divide the current graph that you have in two components basically. So for example, if in this case we remove any of the edges, for example this 1 to 2, you can see there are two components, which is a graph 0 to 1 and a graph 2 to 3, right? So that is basically what it means. So for this problem, what we use is we use a concept called back edge. So a back edge is nothing but an edge going to an ancestor except for the parent itself. So for example, if you are iterating a tree using DFS, so you will first go to this 0, then actually let me make my screen non-black and white right now quickly. So let me say a back edge is going to be in green, right? Let me say a back edge is going to be green, and a tree edge, a normal tree edge, let me write this, tree edge is going to be in red. So to understand the concept of tree edge and back edge better, you can watch a video online. I'll quickly explain my solution. So for example, you are using DFS to iterate this tree. So first you will go from 0 to 1. This will be actually let me edit the normal graph first. let me create another edge like this. For example, I start iterating from 0. I go from 0 to 1. 1 is unvisited, and 1 does not come before 0 in the current DFS search, you can say. So we'll mark it with red. It will be a tree edge. Similarly, from 1 to 2, we'll mark it as red. It is a tree edge. Similarly, you can go from 2 to 3. You can mark it as red. It is a tree edge. But with this edge from 2 to 0, now we can see that 0 is already visited, and 0 is not the parent of 2, right? Because the parent of 2 is 1 in this case. So since it is not the parent of 2 and it has already been visited, which means it is an ancestor of 2 and not a parent of it. So you can mark it in green. It basically means that it is a back edge. That is basically how this works. So that is the concept of back edge, and using this back edge you can find out if an edge is a bridge edge or not. For example, let me give you a better example. For example, we have this 0, we have 1, and we have any kind of subtree right here, right? Just a second. And we have any kind of subtree right here. This is a subtree. So if I were to, for example, remove this edge from 1, right, then what we see is we can divide it into two components, right? One is going to be this bottom triangle, which is a subtree, and one is going to be this one, which is 0 and 1, right? One is going to be this, and one is going to be this. So you are dividing it into two components. But if from this subtree, for example, you have another edge coming backwards like this, right? So what if I were to remove this edge 0 and 1? As you can see, even if I remove this edge 0 and 1, we still have a way of reaching this subtree from this 0, or you can say we have a way to reach both of these graphs, or you can say both of these separate graphs are connected still. So they are not actually separate graphs, they are not separate connected components. They are both together, they are connected as one, right? You can reach from one to another. So this right here is a back edge. So that is basically why a back edge matters. So if there is a back edge in the subtree, that means you will still be able to reach that edge, right? So for example, in this we are talking about subtree of 1. So if the subtree of 1 has a back edge going towards an ancestor of 1, except 1 itself obviously. So if it has a back edge, that means you will be able to reach it. That means if you remove this edge from 0 to this, from 1 to this subtree, this edge right here, this one, this edge right here, if you were to remove this edge, then you will still be able to reach each other, right? So that means this is not a bridge. So that is the basic concept behind it. So what we do for this is we keep two things, obviously more than two things. The first one is your normal node itself. You can call it U if you want to, or you can also call it a node, right? Okay, let me write it like this. Either call it node or U, and you can have a parent node. In this case we also need a parent node. Why? Because I've already explained it. Because a back edge is any edge to its ancestor except for the parent itself. So that is why we need the parent as well, so that we can check if the edge itself is not going to the parent itself. That is why we need this parent node, right? And we need a V, which is going to be your neighbor basically, right? Your neighbor. And other than these three, these are just variables, you can say variables. Other than these three, we need a couple of vertices. Obviously one is going to be your visited, as usual it is needed since we are using DFS. The next is going to be one called discovery. Now this vertex is called discovery. Why? It is storing the discovery time that we get for each node, right? So for example, first you are going to the first node, so its discovery time is going to be 1, for example. Then you go to the second one, its discovery time is going to be 2, then the third one is going to be 3, like that. Basically, I will explain it by dry run quickly in a second. And other than that, you need a low vertex. Now this is where I have been stuck for days, because any kind of solution I've been looking at online, I don't know where they read their solutions, but all of them have been saying that this is the lowest time to reach a node. This is the lowest time to reach a node. Now, this has been confusing me for days, because the algorithm itself has not been making enough sense to me with how it has been working. So I will write what it is right now. It is not the lowest time to reach a node. It's the time to the earliest ancestor, basically discovery time of the earliest ancestor of V, except U, obviously, because U is going to be the parent itself, except U. Discovery time of the earliest ancestor of V except U, that can be reached via a back. Just an update. In this, I might have made a little bit of a mistake to say what I mean. When I say V in this, when I'm explaining what the low vertex is basically storing, so when I say V, I don't mean the neighbor of U, I mean the subtree of U, right? So I mean the subtree of U in this case instead of its neighbor V. So in this, I will try my best to edit most of it so that you can see the right explanation written on top of this edited one, written on top of this one in Paint, basically. So just so you understand, it is the discovery time of the earliest node of the subtree of U, you can say, of the discovery time of the earliest ancestor of the subtree of U. That is basically what it means. So yeah, now we can just move on to the solution. Now we can just continue. So let me quickly underline the keywords, kind of, you can say, and a back edge, right? So that is basically what it is. So it is the discovery time of the earliest ancestor of V except its parent that can be reached via a back edge from V. Let me write from V. From V to ancestor. That is basically what it is. Now, all of the solutions online, I don't know what kind of weed they are smoking, but all of them have been saying this is the earliest time to reach V, earliest time to reach V. That is just like the stupidest thing to say, you can kind of say. Even I can kind of tell that the algo itself is not clear to them either. They have just kind of crammed it up and just memorized the algorithm instead of trying to fully understand it. So I will quickly explain. I will dry run this algorithm on this graph right here, this one, this graph right here. Let me delete the other one or just move it away quickly. Yeah. So let me dry run. Now what do we need? We need the node itself, the parent, the neighbor, right? So let me write all of it right here. For each node, we are going to have a discovery time and a low. Now I will be writing in this pattern on top of each node, you can basically say. So for example, it's going to be 0, 0, like this I'm going to be writing for each node. Or let me just color code it if in case it kind of confuses you. We need this, then we are going to write the node itself, its parent, and its neighbor, right? Now I'm kind of dry running it on the simplest test case, you can say, but simple test cases are really good to understand algorithms, so that's basically it. So we're going to be starting from the node 0. Is it visited? It is not visited yet, right? So let me also create a visited in case it confuses you. Let me create a visited quickly. We have 0, 1, 2, 3. Is it visited yet? No, it is false, right? None of them are visited yet. So they are all false. So what is the parent initially? The parent is -1, the initial node is going to be 0, and then we move on to its neighbor. So first of all, let me update the discovery and the load time for it. So it is going to be 0 initially. And then we look at its neighbor. The first neighbor, it has only one neighbor, which is 1. So we move on to 1 now, and we will mark it as visited, true, right? So then we move on to 1. Let me quickly update this part. Now, so the parent is going to be 0 in this case, the node itself is going to be 1, and we are going to be updating its discovery and load time. So it is still going to be 1 by 1 because we are updating it. Since this is the next position, we update it by 1, right? The discovery time and the lowest time for it, or not the lowest time, as you have already heard. The lowest is basically the time of the discovery time of the ancestor that can be reached by it, right? Using a backage. Since we have not encountered a backage yet, you don't really have to worry about it. So what you do in this is, first of all, you check its neighbor now. Its neighbor is going to be 2 in this case, 2. So you are going to be updating and moving along. You are going to be updating this to true. It is visited. Now the parent is going to be 1. The node itself is going to be 2. Now there are 2 possible neighbors, right? 3 possible neighbors actually. I will explain the other one as well. Why not? If the neighbor is 1, 1 is parent itself, right? So we are just going to skip it. We don't worry about it. Now, if the neighbor is going to be 0, right? The neighbor is going to be 0. You can also go to 3 first, doesn't matter. If the neighbor is going to be 0, then it is already visited, right? It's already visited. Since 0 is already visited, we can update the load time of 2, which is initially 2. Discovery and load time of 2 is initially going to be 2. Now we see that there is an ancestor except its parent that can be reached using the backend. So we are going to be updating its load time by the discovery time of that parent, which is going to be 0, right? Because you can reach it from that ancestor. Now we'll move on to its other node, which is going to be 3. Now its discovery time is going to become 3 by 3. Now you are going to check if it is a backage or not. How do you know if it is a backage? Let us see quickly. How do you know in this if it's a backage? We can clearly see that the low to reach 3 in this case is clearly greater than the discovery, even the discovery time of your node, which is 2, right? The parent node. Now, why this works is, since we are backtracking in it, if for example the backage was from 3 to 0, then it would have already been updated first, right? It would have been updated to 0. Now since low of 3 would have become 0, which would have been greater than the discovery of 2, which is 2, we could have told that it's not a bridge edge because removing this edge doesn't disconnect it into 2 connected components, right? That's basically it. So in this case, you can tell that it is a bridge edge because the low is greater than this, so it means this is a bridge edge, right? So then you can reverse back. You go back to 2. Its low is already updated. Now another thing is that why we are checking with the discovery of the parent, right? You might be wondering. We are checking with the discovery of the parent because its low can be updated in the future, right? As you can see from the backage, but if I came to 3 first, if I came to 3 first, the low of this 2 would have still been 2, right? So if I checked it with it, obviously in this case it would have worked, but let us assume it might not have worked in a case, right? For example, if there was a backage from 3, it would not have worked in that case because the low for 3 would have been anything lower than that in that case, and it would have never worked. So since the low of the parent can be updated in the future, while backtracking. So we check the low of the current node with the discovery of the parent, right? So that is because since the low of the current node would have been completely updated by now, and then you can move back and start checking for it. Since there would have been no other edge to check from this neighboring node, you can say, or the child node, that means its low cannot be updated any further, and since its low is logged, you can check it with the discovery of the parent, right? And the discovery of the parent never changes, it remains the same. So similarly, you will recurse back. Now you are at 2 and 1. You will check if low of 2 is greater than the discovery of 1 or not. Since the low of 2, which is 0, is less than the discovery of 1, which is 1, since 1 is greater than 0 for this case, right? It is not a back edge, not a bridge edge. I'm sorry, it is not a bridge edge. Why? Because this low of the child tells us that it can be reached by an ancestor of this one even, right? Since it can be reached by even an ancestor of this one, that means it removing this bridge edge cannot disconnect the graph, so you will still be able to reach it similarly. And now you are going to be updating the low for this one as well. Why? Because you can the lowest node that can be reached, you can say the discovery of the lowest ancestor for this one that can be reached is 0, right? So you are going to be updating it for this as well. That is basically what it means. So then you are going to be checking it with the 0 as well. Again, the condition fails. That means it is not a bridge edge and it works. So we have found only one bridge edge, which is 2, 2, 3. So that is how the algorithm works. So remember one thing in this that I would exceptionally like to put some emphasis on is this low vector that everybody gets wrong. It is not the lowest time to reach the current vector. It is the lowest, it is the discovery time of the earliest ancestor, or the lowest ancestor you can say. It is the discovery time of the earliest ancestor of the current node that can be reached by that node, except the parent itself. Obviously, parent is also an ancestor, but you don't check it with the parent because the back edge would not work with the parent, because since these are already connected like this, you like this, you can do, however, that would not work because they are already connected in one particular way. That is why it does not work with the parent. So I will quickly explain the code now. Let me show you the code quickly. So in this code, this is the function that was given to us, and we were given a specific edge C and D, and we were supposed to check if that specific edge is a bridge or not, right? And C and D is a vector, for example 1 and 2 in this case. So 1 to 2 is a bridge, we can clearly see that. So what I do is I first obviously created an adjacency list, and I created the discovery and low vectors that we need. The visited, obviously we always need it. We needed the parent variable in this case. You can also create a vector if you want, doesn't matter. A variable works fine in this case, initialized with -1, because initially any initial node will not have any kind of parent anyway. So then we have a timer. As I said, we need to store the discovery time of each node. So initially it is going to be 0. Now we iterate all of the vertices. If they are not visited, then I'm going to be calling this DFS function on it. Let me show you this function. Now this function returns true if the discovered bridge edge is going to be CD, and if the discovered bridge edge is not CD, then it returns false, or keeps checking, you can kind of say. And if no bridge edge is found which is equal to this CD, then it just returns false, right? So if it returns true, that means the bridge edge that we have found is this CD edge, right? So that means you can just directly return true. Otherwise, if you come out of this for loop, you can return false because you have not found any edge like that. So let me quickly go to this function DFS. In DFS, the return type is bool, since we need that for the current question, and we pass in the current node. This is U, basically you can say U, the parent, the adjacency list, the timer, the discovery node, the low node. You have the visited, and I'm also passing C and D in it, so that I can just check if the bridge edge is equal to this edge or not. So first of all, we obviously update the discovery time whenever we reach that node. we update the discovery time to be timer, and then we update the timer by +1. Then you mark the current node as visited, obviously. Then you check all of its neighbor, which is basically v, you can say. So you check for all of its neighbors, and if the neighbor is the parent itself, then you continue, because then you can't do anything about it. If it is the parent itself, then it can never be a bridge edge anyways, and it is already visited, so you can't really do anything about it. So if the neighbor is not visited, then what happens? So if the neighbor is not visited, then first of all we are going to be calling DFS on it the same way we have called it before. If it returns true, then we return true, because then we know that that returned bridge edge is going to be equal to CD, right? So you first of all call DFS on its neighbor, known visited neighbor, and then we are going to be updating the low time for the current node with its neighbor, right? So if the neighbor can be reached by an ancestor from before, that means if we, for example, we have this node 1 and we are checking for this 2, if we can reach this 0, right? So the lowest or the earliest ancestor that can be reached, from which we can reach this 2, is going to be 0, right? So we are going to be updating it for this 1 as well, because we know that the earliest ancestor for it that can be reached is going to be this 0, right? Or basically the earliest node that is connected from the subtree. This is a better way to put it, you can kind of say. So the earliest ancestor of this 1 that is connected to the subtree of 1, right? Let me show you it in Paint quickly. So for example, we have this example, right? Let me quickly move this over here. Yeah. So basically what it means, why we are updating the low of this one is because it gets updated to the ancestor of this one, or the earliest ancestor of this one, that connects both the subtree and the ancestor, you can say. So you can say, let me write it like this: earliest ancestor. Let me copy the condition as well. I have not directly written it. Okay, I will just paste it from the code. Earliest ancestor of the current node that connects the ancestor, or you can kind of say the parent tree. So you can kind of create a tree like this. In this case, for example, you have this one, you have a parent tree going up here, and you have a subtree going down here. So if there is a back edge, you can say like this, that means these two are connected, right? Let me quickly write it like parent tree, or you can call it a child tree or a subtree, whatever you want in this case. So earliest ancestor, or you can say earliest ancestor of the current node that connects the parent tree of the current node with the subtree of the current node. That is basically what it means. So let me make it just a little bit smaller quickly, so that you can see both the graph and this thing together. Like this should work. Yeah. Okay, let me move this a little bit, and let me move this one somewhere around here. Yeah. So this condition is basically what matters, and we have it for the condition. Quickly. for this condition basically, right? So what this condition means is that earliest ancestor, we are assigning its position, its low as the earliest ancestor of this current node that connects the parent tree of the current node and the subtree of the current node basically, right? So that is what basically means in this case. Now let me show you the code again. Let us continue with the code. Now if obviously it assigns it like that, but now since we have backtracked from here, we also have to check if it is a bridge edge or not. So current node and its neighbor, if it is a bridge edge or not. So how do we check it? Is we check if the low of neighbor is greater than the discovery of the current node or not, because if it is, then it is the only way to reach it and there is no back edge that can connect them, right, after removing this bridge edge. So if the low of neighbor is greater than the discovery of node, it's only possible if it is a bridge edge, right? So if then this is the condition to check if it is the given edge or not, the edge that we check. So basically we just check if it is equal to C or D or not, like this, very simple. Then otherwise, if the node is already visited, now since the node is already visited, that means it is clearly a back edge, right? Because we have already passed the condition if it is a parent or not. Since it is not the parent, it has to be a back edge, right? So for that we can just check, since it is a back edge, we can just assign its low as minimum of the low of the current one, and it's the neighbor or the earliest ancestor that we can reach, the discovery of the earliest ancestor that we can reach, right? And then after coming out of this for loop, which means you have checked every other node that can be reached from it and you have not found the bridge itself or the specific bridge that we are trying to find in this problem, then you just return false. So this is the code for it. The code works. I have submitted it, tested it out. It works completely fine. Now the algorithm itself is quite difficult to understand, I would say, because I have been trying to understand it for like the past couple of days. It took me days to understand it fully, because as I said, everyone else teaching it online has been using wrong words for it. So it really matters what you are trying to say. It really matters what you are when you explain an algorithm, it really matters what you are saying or how you understand it and explain it to other people. If you use wrong words, for example, the lowest time to reach the edge, then yeah, the algorithm is always going to be unclear. That means you are just cramming up the algorithm, not actually understanding it. So I hope I was able to make you all understand the algorithm a little bit better. Obviously, I'm not the best at explaining, but I tried my best explaining the conditions where I got a problem. So hopefully you all also understood it completely. And yeah, so now I will just move on to the next problem. If you want, you can check out other solutions of Tarjan's algorithm online to understand it better. There are other people who might be able to explain it better even. Although I was not really able to find anyone who was able to explain the algorithm correctly. One that I really liked was explanation of Abdul Bari, but he was explaining articulation points, but the algorithm is quite similar, you can say, so you would be able to understand it. And other than Abdul Bari, I don't think I found anyone who was able to explain it well enough, so it took me days to fully understand the algorithm after reading some stuff and trying to understand it myself. So now I will just move on to the next problem, which is maybe going to be articulation points in a graph. So I'll just move on to that. I will mute myself again. Again, I might make my screen black and white, so if you don't like it, sorry about it. Now I'll just move on to the next problem. So I have solved the next problem as well. In this we had to find articulation points in a graph, and it is quite similar to the bridge algorithm. So let me first explain what an articulation point is. I think it is already written in this problem. Okay, it is not written in the problem, but articulation point is basically any kind of vertex in your graph, removing which the whole graph will be divided into two separate components, two or more components you can say. So that single vertex is the articulation point. For example, in this test case that we are given, 1 is an articulation point because if you remove 1, 0 will be a separate component, and 1, 3, 2 and 4 is going to be a separate component, as we can see right here. Another one is 4. If you were to remove 4 from here, 0 and 1 would be a separate component and 3 and 2 will be a separate component, as we have seen right here. So that is what an articulation point is basically. So the overall algorithm is quite similar to the bridge algorithm that we have already done. I will show you the difference between the two. So the only difference is actually this part right here. As you can see, in bridge algorithm we were doing if the law of the neighbor is greater than the discovery of the node, right? But in this case we are doing greater than equal to. And why that works is basically, let me show you in Paint quickly. So let me quickly show you. For example, we have this set of ancestors, you can say. We have this edge u, it is connected to a neighboring edge v, and it has a subtree like this. So the condition for the bridge algorithm was, let me quickly write it. Bridge condition was law of v should be greater than discovery of u, right? Now why this condition, like why not greater than equals to for bridge algorithm? So that is basically because law of v is basically you can say the ancestor of u that can be reached by the subtree of v, right? So the lowest ancestor of u that can be reached by subtree of v. So any ancestor that can be reached in this is what law v basically is. But if it is greater than equal to u, then it will also be checking if that subtree is able to reach this u or not. So if it is greater than equal to discovery time, so for example, if it is equal to as well, if you put it equals to, then it will be checking for this u as well, right? Greater than equals to this discovery of u, which means the law can be equal to this discovery of u, which means we can reach this u, not the ancestor of u, but this u from the subtree of v. Now since we can reach this u from the subtree of v, let me quickly edit this. Since we can reach this u from the subtree of v, if we were to remove this edge from u to v, it is still connected, right? So that does not work because it is not dividing into two separate components. So instead of that, we keep it only greater than u, so that it will be checking for the parent of u basically, right? That is it. Or let me give a better explanation. So since we want this u comma v, let's say this edge u comma v to be a bridge, so it can only be a bridge in one case, if the law of this v is greater than the discovery of u. So if it is like less than equals to discovery of u, for example, if it is less than equals to discovery of u, that means that we can reach any ancestor of u or u itself, right? And for all these conditions, if we remove this edge u comma v, then we won't be disconnecting the graph. That is the reason why we take the condition of law v strictly greater than discovery of u, because that is the only way in which removing this edge u comma v is going to result in two or more separate components in the graph. So that is the reason why. Now for an articulation point, why do we take law of v greater than equals to discovery of u, right? So if we were to check with this condition low v greater than equals to discovery of u, so first of all let us take the cases where this condition is false, right? So if low v is less than discovery of u, so for it to be less than discovery of u, we should be able to reach the ancestors of u from the subtree of v. So the only case would be like this, right? Now in that case, if for example you were to remove u, let me quickly remove u, just a second. If you were to remove u, you will still be able to reach both the components, right, from one another. So it would not work because we can reach it. But what if instead of that we were to reach like till about u, right? So that is basically what this condition is, low v greater than equal to discovery of u. So we can reach u or anything or after it basically, right? So it won't be reaching any ancestor of u, any subtree of v won't be reaching any ancestor of u. Then in that case, if we were to remove this u, then what will happen? We will be disconnecting this edge which is connecting the parents, we will be disconnecting the edge connecting with v, and we will also be disconnecting this edge which is connecting it to its subtree right here, right? So that is basically the reason why this condition works, because even if it is like equal to that u itself and we are checking for that node u specifically, so removing it already disconnects the graph into two or more components. Unlike bridge, in bridge we cared about an edge from u to v. Here we only care about a particular node. We are checking for a specific node if removing that will disconnect the graph or not. So that is the reason why this greater than equal to condition works here and why it does not work with the bridge. Because in bridge we are just removing an edge, not that point itself. That is the reason why the greater than equal to condition would not work with the bridge. But with articulation point, this greater than equal to condition works. So that is basically the explanation of that. Now let me explain the code quickly, although the code is going to be of course similar to what we have already seen. We just basically apply normal DFS to it. So you have a visited vector, discovery. There is another condition by the way for articulation points. Let me quickly tell you that as well. Yeah, so another condition for articulation point is for the root. So how do you check if the root is the articulation point or not, right? So you might be wondering that we can just use this condition for example, but for any law of v, or basically for any neighbor of root, the law cannot reach its parent because the parent of root is going to be -1 always. There is no parent of the root itself. So how do you check if the root itself is an articulation point or not? So the simplest way to check it, if that, for example, we have this root r and we have all of these particular kind of trees with it, right, in DFS tree. So if r has more than 2 children or greater than equals to 2 children, you can say 2 children, right? If the root has, let me write it correctly, just a second. Root have greater than equals to 2 children, and in that case, if we were to remove this root right here, then we can see it directly divides into 3 separate components. For example, there were 3 children in this. Similarly with 2, it will be dividing into 2 separate components. But if there is only one, then removing the root will only divide it into a single component. So that is the reason why this works. And another thing is that a condition where I was really confused is why does this thing work with the root, right? For example, if we have this root right here and we have its children like this, then I was thinking, what if there is a cross edge between these two children, right? Because if there is a cross edge between these two children, then even after removing the root, they will have a connection in between them, right? So that is basically where DFS comes in, because we are applying DFS. So we will check for the root condition having greater than or equals to two children after DFS call has finished on the root, right? So after DFS call has finished on the root and we have returned to the root, then we will know how many distinct trees this root has. Because if, for example, there was an edge connecting these two subtrees of R by a cross edge, then in that case it would have returned this whole thing. Let me quickly show it like this whole thing as a single tree, right? This would have been a single tree, because in DFS call you would have already checked out this tree and you would not have visited it again from R, right? So that is basically the reason why this works. So if the root, so this is why the DFS algo works in this. You use DFS, and by the end of the call you just check if the root has greater than or equals to two children or not. If it does, then in that case it is an articulation point as well. Now let me quickly show you the algo. Algo is quite like, it's not anything exceptional. So we have this visited vector v, discovery, low. I'm also keep creating this vector called articulation point. I just mark it to true if it is an articulation point, and it is only because we need the result in sorted order. So if we just directly store all the vertices in result, for example, if there are v number of articulation points, then in that case, if we sort the result, it is going to be v log v, right? That takes a lot of time. So why not I just create a vector like this called AP. I'll just mark each one as visited, and at the end of my algorithm I can just iterate it from the initial vertex to the last vertex in sorted order and keep adding them to the result as articulation points. So that is the only reason why I'm using it. I have this result vector as well. Then I just call this for loop. If it is not visited, I call DFS on it. There is going to be only one case with the root, right? And its parent is going to be -1. That is this -1 right here. Then in the algorithm, first of all, I'm marking visited as true. I am marking discovery of node and lower node as timer, basically, and then updating that timer. So it is globally defined like this, the timer. Then I'm also keeping this children variable. This is to check how many children does this node have, and we will only need to worry about this in case it is the root. So but you can define it for all, doesn't really matter much. So then I iterate all of the neighbors. If the neighbor is the parent itself, you just ignore it. If it is not visited, then we are going to be applying DFS on it. As it returns, it is going to be updating the low of neighbor. We know that. So we are going to be updating the low of our node from this low of neighbor. And then we just check for the articulation point condition. So if the neighbor is greater than or equals to discovery of node, and its parent is not -1, because if its parent is -1, then it basically means that it is the root, and removing it would not really make a difference, right, in that case. So that is basically what it means. And then we can just mark off its articulation point as true and update children ++. So this children is being updated whenever we encounter a not visited neighbor for the current node, because for DFS call it would have already been marked visited if it was reachable from other neighbors. So that is basically why we can update it. And if that node is already visited, then we can just update the low of this node using the discovery of neighbor. And at the end you just check if the parent is -1 and children is greater than 1 or not, because that is the root articulation point condition. And if it is true, then you just mark the root articulation point as true as well. That is basically it. Then after returning from this algorithm, you just iterate all of these points in AP. If they are true, you just append them to result. If nothing is appended to the result, then you just append -1 in that case because there is no articulation point, and then you just return this result. So I've already compiled and run this code. It works completely fine. Let me submit it as well. Now on Geeks for Geeks, there are two articulation points questions, and both are completely similar, and the algo works for both. So I think the only real difference between the two is that it has less number of test cases, only 165, while this other one, articulation point 2, I have used the same algorithm in this, and it works completely fine. I think this one has about more than 1,000 test cases, but the algorithm is completely fine. It works on this as well. So yeah, that is it. So this was my solution for finding articulation points in a graph. Not my solution, but my explanation for the solution. It is Tarjan's solution in reality. But anyways, so now we can just move on to the next problem. Okay, so I have solved the next problem as well. In this problem, we had to find the strongly connected components in a graph using the Kosaraju algorithm. So I will first explain what is a strongly connected component, then I will explain how the Kosaraju algorithm works, then I will explain why it works, and then I will show you guys the code. So first of all is a strongly connected component. So a strongly connected component is a set of vertices in which every vertex can be reached by every other vertex. So for example, if we take 0, 1 and 2 in this, right? 0, 1 and 2 in this graph. So can we reach 0 from 2 and 1? Yes, we can reach 0 from both 2 and 1. We can go from 2 to 1, then 1 to 2, 1 to 0. Similarly, we can reach 2 from 1 and 0, and we can reach 1 from 0 and 2. So in this set of vertices, which is 0, 1 and 2, we can reach every vertex from every other vertex, right? So that is a strongly connected component. So similarly, 3 alone is going to be a strongly connected component. Why? Because from 3 you can reach 4, but you cannot reach 3 again, right? So 3 is going to be a strongly connected component by itself. Similarly, from 4 you cannot reach any other vertex, so 4 is going to be a strongly connected component itself. Because you can basically say it in a sense like you can reach a vertex by that vertex itself. For example, if you are standing at 3, then you can reach 3, right? Because you are already at 3. So that you can kind of think of it in that way. So how Kosaraju algorithm works for this is, first we find the topological sort ordering of these elements and put it in a stack. Then what we do is we reverse these edges. So for example, we are going from 0 to 3, we will reverse it and we will go from 3 to 0. Similarly, we will go from 4 to 3 and 2 to 0. So you will be reversing every single edge in this, right? I'm sorry, I might have said vertex. Edge, you will be reversing every single edge in the graph. So first you find the topological sort ordering, then you reverse all of the edges in the graph, then you start popping from the topological sorted stack, and you run DFS on it again, and using that you can find the strongly connected component. So basically whenever you pop from the stack, all the elements you can reach from that single vertex are part of a single connected component, you can say. So for example, if you are to start from 0 in topological sort ordering, in the topological sorted stack, 0 is going to be on top, right? If 0 is on top and we pop from 0 and all the edges are reversed, so we won't be able to go from 0 to 3, but we will be able to go from 0 to 1, then 1 to 2, then 2 to 0, right? So from 0 we will be able to reach 1 and 2. So these 3 are going to be part of a single connected component. Similarly, 3 is going to be a single connected component, and 4 is going to be a single connected component. Now I will explain why the algorithm works using paint. So how does topological sort ordering works? So you have all of these elements, you can say. What will happen in this is every element that comes after the current element is going to be coming after that element in the topological sort, right? So that is the way topological sorting works. So basically, if we have just a second, 1, then 2, then 3, and then 4. So the topological sort for this is going to look something like 1, 2, 3, and 4. So basically, since 4 is coming after 3, it will come after 3 no matter what. It will come after 2 no matter what. It will come after 1 no matter what. Similarly, it will come after 3, and similarly 3 will come after 2 and 1, and 2 will come after 1. So that is basically topological sort, right? You might have already learned it in either one of my previous videos, or you might have seen it already. So finding a strongly connected component can be done using topological sort. And why that is because, for example, let us say this is a single strongly connected component, right? And let us say this is another strongly connected component. So these are two strongly connected components. Let me call this C1, let me call this C2. And there cannot be an edge going from C2 to C1 no matter what. Why is that? That is because if an edge is going from C2 to C1, then this whole thing will be a strongly connected component by itself, right? So that is the reason why an edge cannot go from C2 to C1. So if we were to do, for example, topological sort on this, we know that C1, that strongly connected component C1, is going to be coming before C2, right? So if I was to create topological sort stack and I was to run topological sort algorithm on this, first it will go to C1, from C1 to C2, and when it is backtracking from C2, it will be adding C2 to your stack, and then it will be adding C1 to your stack. By the way, notice that C1 and C2 are not necessarily just a single vertex. It can be a set of vertex. So note that in the topological sort ordering. So what happens if I were to reverse the edge now, right? So if I reverse the edge, we will be going from C2 to C1, right? And in topological sort, C1 is on top, so you will first pop out C1. C1 is popped out, and you will run DFS on it. Now from C1 you won't be able to reach C2, right? So you will be able to reach all of the elements that are inside this C1, all of the vertices inside this C1. So when you return from it, you will know that this is a single connected component because you cannot reach any other connected component from this. So what happens with the algorithm is basically, when you're doing a topological sort, you are getting a topological sorting of the vertices, but you are also getting a topological sorting of the strongly connected components themselves. So you are getting topological sorted ordering of a set of vertices, you can say. So from there onwards, you can start applying the reverse graph algorithm, because any set of vertex we are going to reach, for example, we can reach this, we can reach this, we can reach this, we can reach this, right? So if we were to reverse the edges in this, what will it look like? Let me quickly reverse the edges in this. Okay, there we go. It will look like this, right? But this vertex itself is going to be the first one in topological sort. And when you pop it out and run DFS on it again, it won't be able to reach any other vertex. Similarly, if, for example, this is going to be the next vertex, you won't be able to reach one from it, and you won't be able to reach any other vertex because one is already visited and you cannot reach any other vertex. So this will be a single connected component. So when you get topological sorted ordering of a set of vertices and you reverse the edges from it, then you will be able to find that since the topological sorted ordering is reversed now, right? The topological sort ordering was this initially, but since it is reversed, since all of the edges are reversed now, the real topological sorted ordering should look like this, C1 and C2, but it is reversed now. Since it is reversed, you will be popping C1 first, and since it is the last element, And we have already defined that for each element, all of the elements coming before it should come before it in topological sorted ordering. But since the edges are reversed now and this is the topmost element, C1, all of the elements that were coming before it, now they will come after it, basically, right? Because it is reversed. Since they will come after it now, you won't be able to reach those other connected components, and so this is a single connected component that you will be able to find. Similarly with C2, when you run the algorithm on C2. So that is the way it will work. I know my explanation might not have been the best. You can definitely check out other solutions. The algorithm is quite simple, and I think once you understand why it works the way it works, it is quite intuitive as well. So now let me explain the code that I have written for it. It is really simple. We will go step by step. So the first step was to find the topological sort ordering, right? So I created the visited vector, I created the topological sorted stack, and I ran DFS on it. This is my normal DFS function, and in the end, whenever we are backtracking, we will be pushing the current node to the stack. That way we will be able to find the topological sorted ordering. What is the next step? After finding the topological sort, what we have to do is we have to reverse the adjacency list. So basically we have to reverse the edges of all the vertices, right? So that is basically what we do here. I am just creating another adjacency list. You can also do it in the original one, doesn't matter. And I am also resetting the visited vector because of course now all of the elements are visited from the previous topological sort call. So we have to reset it. So I am just resetting it as well, and I am creating a new reversed edges adjacency list, right? Then we find strongly connected components using a count, and we pop from the stack. We run the while loop until the stack is empty, and if that node is unvisited, then we know it is part of a strongly connected component. So you will be updating the count and you will be calling reverse DFS on it. Reverse DFS is nothing, just normal DFS, just on reverse edges. So since the adjacency list is already reversed, you don't have to worry about that. And that is how we solve this problem to find strongly connected components using the Kosaraju algorithm. Now this code works well. I've already tested it out. I'm able to submit it for all the test cases as well. Let us see this quickly. Yep, so this works completely fine. Now the algorithm is pretty easy, and the intuition is also easy once you understand why everything is happening the way it is happening. And the time complexities in this case is going to be linear because we are basically doing DFS, nothing more than that. So it is linear, and space complexity as well. We are only creating the stack for topological sort of order V. So that is basically the space complexity as well. So it is also linear. So this was my solution for strongly connected component for using Kosaraju algorithm. Now I will move on to the next problem. Okay, so I have solved the next problem as well. This problem was finding the shortest path in a graph with negative weights using the Bellman-Ford algorithm. So why, first of all, the question might arise is why we cannot use Dijkstra's algorithm to find shortest path with negative weights, right? The simplest answer to it is that Dijkstra's algorithm will pick the closest vertex, non-negative of course, since it does not work on graphs with negative weight. So it will pick the closest vertex and it never revisits it, right? But due to negative edges, there is a possibility that you can later on find a path that is smaller than the current path. Let me show you that with an example quickly on Paint, of course. So for example, this is the source node that we are starting from, and let us say this is the destination node, right? Let me write it like this. This is the destination node. And we have this node in between. Let me quickly just erase this. Yeah. So let us say we have this directed graph, for example, or it can be an undirected graph as you wish. I'm just making directed to make it simpler. And let us give edge weights of 2, 2 and -1 over here, right? So if we were to run Dijkstra on this, from S we will go to this node U and to D, and it will mark D as visited. So it will say the minimum distance to the destination node is going to be 2. But if we were to come from U to D, then it will be 2 plus -1, which is going to be equal to 1. Now this is shorter than the previous path, but since D is already visited, we won't be checking for it, and we won't be finding the actual shortest path. So that is why Dijkstra's algorithm basically fails for this. So we have to use Bellman-Ford algorithm, and this algorithm Bellman-Ford algorithm is used for two things, not just for finding shortest path, but also to find if there is a negative cycle in the graph. Now I will explain in a bit why it is like that, or I can give you the simplest explanation. It is because with a negative cycle you can kind of get stuck in an infinite loop, you can say. So that is the reason why it does not work with negative cycles. For example, let me show you an example in this. Yeah, for example, this path, if you, for example, go from 1 to 2, it will be -6 distance, then 5 is going to be -6 plus 5, 1, -2 is going to be 1 minus 2 is going to be -1, and then from 1 you can again go to 2 and the distance can decrease. So it will decrease. For example, we have -1 till here, then from -6 it will go -7 for 2. So this way we can get stuck in an infinite loop. That is the reason why this algorithm does two things. It first of all will check if there is a cycle or not, and if there is no cycle, then it will be returning the shortest path. That is basically how this algorithm works. So let me first explain how the algorithm works, or what we do in the algorithm, then I will explain why it works. So let me go back to Paint quickly. So there is a condition in this that we have to use. So let us say we have an edge from U to V, right? And there is a condition that we have to check for each edge. That condition is if the distance till U plus this W is less than the distance of this V, then what we do is we update the distance of this V with this. That is it basically. So if this, then you do this. But this whole thing, for each edge you have to do this capital V -1 times, or number of vertices -1 times. Now why that is because let me quickly explain this. So let me make another random graph. For example, this can be any graph, doesn't really matter what kind of graph. You can make whatever you want. So in this graph we are starting from the node S, and we are going to be defining its distance as 0, right? Because obviously the first element, the distance of the vertex itself, is going to be 0. This is the source vertex, you can say. It can be any vertex in the graph that we are starting from, that we are given, from which we have to find distance of other vertices. So this is the relaxation condition, right? This whole condition. This right here is the relaxation condition. Let me write it. Relaxation. So if you were to run this algorithm for the first time, let us say the first iteration, what will happen? what will happen is that from S you can have multiple vertices u, v up to so on, right? Or let me kind of write it like v1, v2, kind of like this, right? So on the first iteration, if we were to use this relaxation condition, then what will happen is for each of these edges or each of these vertices v1, v2, the distance is going to be updating to 0 plus w1. For this it is going to be 0 plus w2 and so on, right? But the edges after these, for example, if we have an edge u1 here, then there is a possibility that there is some other vertex. Let me just quickly move this a little bit. Yeah. So there is a possibility there is some other vertex, for example, from here, from which we might be able to reach u1, right? Or it could be any other vertex from which we are able to reach this u1, and the distance from this is shorter because there might be a negative edge present in between anywhere, right? So what we notice from this is the next set of vertices from S, we are able to find their minimum distance from S in the first iteration, right? So in the first iteration, we have defined the distance for all of these vertices, or we have found their minimum distance. Found minimum distance from S in first iteration. Or let me show you with a better graph, I can kind of say. Let us kind of create a level order graph, right? So if you have this node S here and all of these, now there can be any edges from in between, in like going like this, any edges jumping back from anywhere, anything is possible, right? So what you do is on the first iteration, if you were to apply this relaxation condition, you know for sure that for this first layer of vertices from S, you are going to be getting its minimum distance according to this condition, right? Because from there is no vertex before S from which we can reach this vertex V1, right? With a distance of 0 from S. So from here, with a distance of S from to these first sets of vertices, you can see. And similarly with the second iteration, you will find distance to the second layer, you can say, kind of, right? Of course you can keep revisiting vertices and updating distances and stuff, but we know for sure edges with at most one edge in their shortest path, which is going to be these edges with at most one edge in their shortest path is going to be calculated in the first iteration. Similarly, edges with at most two edges, coming from the first layer, of course, with at most two edges will be found in the second iteration at most, right? You can find lesser ones as well again, and you can find future ones as well, but it is not guaranteed that you will find the ones with more than two edges in the second iteration. So that is basically what you do. You, in each time, you are going to be finding the vertices with their n. For example, if it is the ith iteration, you will be finding the vertices, the shortest part two vertices that have at most I edges in their shortest path, right? I might have said minimum distance before. It is not exactly minimum distance. That first edge, you can say, in their shortest path, one edge in the shortest path, right? You will be able to find them. Of course, there might be more. For example, in this graph, there might be more edges from which you can like come back here, and it can be negative, so it can decrease. But you know, at least for some of these edges, at most you have find the ones with one edge, right? Or it can be lesser, of course. So with ith iteration, let me quickly delete this. With ith iteration, you have found shortest paths with at most I edges, right? And this basically tells us why we have to do v minus 1 times, why we have to run the relaxation condition v minus 1 times. It is because in a shortest path in a graph there can be at most v minus 1 edges, right? Because for example you can have any number of nodes here, and as you can see there are 3 edges, so the number of edges in the shortest path can be at most v minus 1. That is why you run the algorithm v minus 1 times, because by the end you would have found the edges that have their minimum shortest path with the minimum number of edges is v minus 1, right? So you would have found the minimum distance for all the edges by v minus 1th iteration, and after that you will check this condition once again. Why you have to do that is that on the vth iteration, if the relaxation condition is still working, or if you are still able to relax for a few vertices, then in that case you know that a negative cycle is present, because it should not be possible to relax further, because we have found the shortest path to all of the nodes by v minus 1th iteration. So if you are able to find a shorter path on vth iteration, then you know that a negative cycle might be present or should be present definitely, because this should not be possible on vth iteration. Relaxation should not be possible on vth iteration. That is how we can tell if a cycle is present or not. So if this condition still work, a cycle is present, you can just return -1. Otherwise you can just return the distance vector to all of the vertices, or if it is a specific node, you can return the distance to that specific node, because by v minus 1th iteration we would have found that distance, right? So that is how Bellman-Ford algorithm works, and I think my explanation might not have been the clearest of this, but the basic idea that you have to remember is that we are not marking vectors as visited in this case. We can revisit the vectors in the future and update their distance using this relaxation condition, and we run this relaxation condition on each edge v minus 1 times, and by v minus 1 at time we should be able to find the shortest path for each vertex if a negative cycle is not present. And to check if a negative cycle is present, we will run it one more time, which is the vth iteration. And on the vth iteration, if the condition is still working, if you are still able to relax the distance for any vertex, then you know a negative cycle is present, and in that case you can just return -1. Otherwise you know that if a negative cycle is not present, then you know that the shortest path should have been found, and then you can just return the shortest path which is stored in this distance, basically, right? Now my explanation might not have been the clearest. You can check out other solutions online, although I was not able to actually find a solution that would explain why the algorithm works. All of them kind of just explained how the algorithm works. So hopefully you will be able to understand it. Now I will tell you how the code works quickly. So in this code, first of all, I have defined a vector distance, and I have given it a maximum value possible. In this case I have given it 1e8 because the question was asking that. You can also give it int max or 1e9, doesn't really matter, just infinite value, because we are trying to find the most minimum value for distance. And you can define the distance for the source as 0, because we are trying to find the distance from the source itself. Then you run the algorithm v minus 1 times. This is the condition to run it v minus 1 times, and this is the relaxation being run on each edge. So we go to each edge in this edge list, we take that edge with the weight, we check if the distance is not this infinity distance, And if it is not, then we can just check if the relaxation condition is valid or not. If the relaxation condition is valid, then you can update the distance, or you can say you can relax the distance for the vertex V. Now, after that, we have to check if a negative cycle is present or not. For that, I've just created this variable negative cycle, and if the condition still works, this relaxation condition is still valid, then you know a negative cycle has been found. In that case, you can just break and return a -1. Otherwise, you can just return the distance vector. Also, let me clarify why the relaxation condition works. So, you can say if, for example, we have found the best path to any edge u, right? If you have found the best path to any edge u, and from that u to v there is an edge, and that edge could be anything, w for example, with weight w. So, if you have found the best known path to u, and you know it uses about k edges, right? Then you know that the best known path to v will be using k-1 edges no matter what from u, right? That is basically how relaxation condition works. Each time the relaxation condition is going to be increasing your shortest path by one edge, and I've already explained how it increases by one edge in each iteration. I initially falsely said it as the minimum distance. Instead of that, it is the minimum number of edges to the next minimum path, you can say, right? And so we run it for v-1 time, since the shortest path can have at max v-1 edges. And then you can just check for the cycle on vth iteration, and if cycle is not present, you can just return. So that is how Bellman-Ford algorithm works. I think my explanation for it might not have been the clearest. You can check other people's solution online. I have run this code, I have submitted this code. It works completely fine, as you should be able to see right now. Yeah, so the code works completely fine. This was Bellman-Ford algorithm. Now, I think now it is complete. All of my graph algorithm practice is complete. Now I will be doing graph questions on lead code or something to practice more. So stay tuned for that, and have a good day. Bye. Also, one thing I forgot to add is the time complexity of Bellman-Ford algorithm. So the time complexity for it is going to be O of V times C, because you are running v-1 iteration for each edge, so it is going to be O of v times C. And if you were to talk about the space complexity, since we are creating a distance vector of size v, then the space complexity is going to be linear. It is going to be O of v, right? Now I have also created my own personal short notes on all of the algorithms. I will be sharing them in the description as well, so you can go and check them out. And yeah, now I will just move on to questions questions on graphs on lead code or something. And so stay tuned for that, and have a good day. Bye.